Far out in the universe, there are stars that break all the rules. They shine too brightly, live too long, burn too hot, or even exist in places where no star should ever be. These stars confuse scientists, challenge what we thought we knew about space, and seem to defy the very laws of physics. Some are leftovers from the early universe that should have died billions of years ago. Others are so massive and strange, it's a mystery how they even formed. These are not just rare, they are terrifying. Before we begin, let us know where in the world you're watching from and what time it is for you right now. Now, settle in for a journey to the most horrifying stars in the universe. The life of a star is a long, dramatic, and truly amazing journey that unfolds slowly across the endless stretch of time. This long story, called the life cycle of a star, tells how a star is born, how it changes as it ages, and how it eventually comes to an end. What path a star follows in life depends almost entirely on how big and heavy it is when it forms. The biggest and most massive stars are like wildfires. They shine incredibly bright but burn out very quickly, living only for a few million years. On the other hand, the smallest and lightest stars are like steady campfires. They burn their fuel slowly and can shine for trillions of years, far longer than the current age of the universe, which scientists believe is only about 14 billion years old. All stars begin their lives in enormous, cold and dark clouds made of gas and dust. These clouds are called nebulae, or more precisely giant molecular clouds. Some of them are truly massive, stretching over 100 light-years across and weighing up to 6 million times as much as our Sun. Inside these huge clouds, gravity slowly starts pulling the gas together. As the gas collapses inward, it breaks into smaller parts. Each part starts to shrink and heat up, eventually forming a glowing ball of hot gas called a protostar. These protostars are like baby stars wrapped in a thick blanket of gas and dust. Because they're hidden in these blankets, we need infrared telescopes like NASA's Wide Field Infrared Survey Explorer, or WISE, to see them. As a protostar keeps pulling in more gas and dust from its surroundings, it grows bigger and hotter. Eventually it becomes stable and enters the main part of its life, called the main sequence. When a star reaches the main sequence, it's officially a full-grown star. During this long phase, the star shines by fusing hydrogen atoms into helium deep in its core. This process, called nuclear fusion, releases huge amounts of energy, and that's what makes the star glow. How long this phase lasts depends on the star's mass. A star the size of our Sun, what astronomers call one solar mass, can shine steadily for about 10 billion years. Smaller stars like red dwarfs burn fuel so slowly that they can live for hundreds of billions or even trillions of years. But the biggest stars, those many times heavier than the Sun, can run through all their fuel in just a few million years. Once the hydrogen in a star's core is mostly gone, things start to change. In stars like the Sun, hydrogen fusion continues in a thin layer around the core, which is now full of helium. This causes the star's outer layers to swell up and cool down, turning it into a red giant. At this point, the star may begin fusing helium in its core. Bigger stars can go even further, fusing heavier elements like carbon, oxygen and others, one layer after another, like the layers of an onion. The way a star dies depends once again on its size. Stars like our Sun end their lives quietly. When they run out of fuel, they puff off their outer layers into space, creating a beautiful glowing cloud called a planetary nebula. What's left behind is the star's core, which becomes a white dwarf, a small, incredibly dense and hot ball that slowly cools over billions of years. But stars that are about 10 times heavier than the Sun or more die in a much more violent way. When their fuel runs out, their cores collapse in just a moment. This collapse causes a powerful explosion called a supernova. After the explosion, all that's left is either a neutron star, a tiny, super-dense object, or, if the star was massive enough, a black hole, a region of space where gravity is so strong that not even light can escape. Some tiny protostars never get big enough to become true stars. If they have less than about 8% of the Sun's mass, they never reach the temperature needed to fuse hydrogen in their cores. These are called brown dwarfs. Some brown dwarfs are just big enough to fuse a rare kind of hydrogen called deuterium for a short while, but they never shine as brightly as real stars. Instead, they glow faintly and cool off slowly over hundreds of millions of years. Even smaller objects, less than 13 times the mass of Jupiter, are called sub-brown dwarfs, unless they orbit a star, in which case they are classified as planets. Inside those giant clouds of gas where stars are born, astronomers have seen long threads of dense gas called filaments. These filaments often break up into smaller, tightly packed chunks called gravitational cores, which are the direct building blocks of new stars. In some filaments, astronomers have discovered neat chains of these cores, spaced out like beads on a string. Sometimes these cores contain pairs of baby stars that shoot out narrow jets of gas as they grow. As a protostar continues to grow and get hotter, the temperature in its core eventually reaches around 10 million degrees Kelvin. That's hot enough to start hydrogen fusion. In stars like the Sun, or smaller, fusion mainly happens through a process called the proton-proton chain reaction. In stars just a bit bigger than the Sun, another process called the carbon-nitrogen-oxygen cycle becomes more important. Fusion creates a strong outward pressure that pushes against gravity, keeping the star stable. This balance marks the beginning of the main sequence stage, the longest, most stable part of a star's life. Astronomers use a special chart called the Hertzsprung-Russell diagram to place stars based on how hot and bright they are. Every main sequence star fits somewhere on this chart. Small, cool stars like red dwarfs sit at one end. These stars live the longest. Hot, massive stars called O-type stars are found at the other end. They are incredibly bright but burn out quickly, sometimes in just a few million years. Stars like our Sun, called yellow dwarfs, stay on the main sequence for about 10 billion years, and scientists think the Sun is about halfway through that stage right now. As stars are forming, many of them develop disks of gas and dust spinning around them. These are called protoplanetary disks, and they are the birthplaces of planets. Over time, dust in these disks can clump together to form rocky worlds, gas giants, and entire planetary systems, just like our solar system. Eventually a star uses up the hydrogen fuel in its core, the very stuff that kept it alive. Without the energy from fusion pushing outward, gravity wins and begins to pull the core inward. What happens next depends on the star's mass. If the star is not too heavy, the core might collapse until a strange force called electron degeneracy pressure pushes back, stopping the collapse. If the star is more massive, the core keeps shrinking until it reaches about 100 million degrees Kelvin, hot enough to begin fusing helium instead. Which of these two outcomes happens depends entirely on how massive the star was when it was born. Now, here's something fascinating. For the smallest stars, like red dwarfs, we have never actually seen the end of their lives. That's because the universe is only about 13.8 billion years old, and these stars live far longer than that. Thousands of billions of years! According to what scientists currently believe, a red dwarf that is about 1/10 the mass of the Sun could shine for anywhere between 6 trillion and 12 trillion years. That's 6,000 to 12,000 billion years. Over this immense time, the red dwarf will slowly get brighter and hotter. Eventually it will become a white dwarf, but that change will take hundreds of billions of years more. These stars are special because they don't expand into red giants like larger stars do. Instead, they burn hydrogen so thoroughly and evenly that nearly the entire star gets turned into helium. Some stars are just a bit heavier than others, and many of them grow into large glowing red giants. But not all of these stars are heavy enough to do something truly dramatic, like starting to fuse helium in their cores. These lighter stars still swell up and shine brightly for a while, but they never reach the most intense stage of being a red giant. Instead of exploding or going through wild changes, they slowly fade and shrink down into small, faint stars known as white dwarfs. They take a quieter path, a gentle ending rather than a fiery finale, similar to stars on what astronomers call the post-asymptotic giant branch, but not nearly as bright. However, something different happens once a star is born with more mass, specifically when it starts out with at least 6/10 the mass of the Sun. These so-called mid-sized stars become hot enough in their cores to ignite helium fusion. This opens the door to a more complex and dramatic life after the red giant phase. Stars with masses between about 6/10 and 10 times the mass of the Sun go through a transformation. They leave the main sequence where stars spend most of their lives and grow into giant stars with huge glowing outer layers. These red giants shine with a soft orange or reddish glow and usually fall into spectral class K or M. On the Hertzsprung-Russell diagram, a chart that shows how stars compare in temperature and brightness, red giants appear on the far right side. Some famous red giants include Aldebaran, the brightest star in the constellation Taurus, and Arcturus in the constellation Bootes. Interestingly, these stars go through not just one, but two red giant stages. The first is called the red giant branch. At this point, the star's core is made of helium that isn't fusing yet, while a shell of hydrogen around it keeps burning and adding more helium to the core. Later, after helium fusion begins, the star enters the asymptotic giant branch. By then, the core has become mostly carbon, and fusion is happening in two shells, one burning helium and the other hydrogen. In between these two stages, many stars settle into a phase called the horizontal branch, where helium fuses in the core. A group of these stars shines steadily and is known as the red clump. They're cool, steady-burning K-type giants. When a star runs out of hydrogen in its core, fusion continues in the surrounding shell. This outer hydrogen shell keeps adding more helium to the core, causing it to grow heavier over time. This process can last anywhere from a few million years to over 2 billion years, depending on the mass of the star. During this time, the star becomes larger and cooler, but it doesn't get much dimmer. It stays almost as bright as before. Then a turning point arrives. For stars about the same size as the Sun, the helium core becomes degenerate. This means it no longer acts like normal gas. Instead, it is held up by strange quantum forces known as electron degeneracy pressure. In more massive stars, something else happens. Their outer layers become thicker and cooler, trapping heat inside. In both cases, the burning hydrogen shell around the core becomes hotter and more energetic. This causes the whole star to swell up and rise onto the red giant branch. As the star grows larger, its outer layers start to bubble and churn with convection. This mixing action pulls materials created deep inside the star, like carbon and nitrogen, all the way to the surface. For most stars, this is the first time the hidden products of fusion become visible. Astronomers can spot these changes by analysing the light from the stars. They find unusual ratios of carbon to nitrogen and different types, isotopes, of hydrogen and helium, especially from the CNO cycle, a special path of fusion. During the red giant branch phase, the helium core continues to grow in size and temperature. Because it's not yet in balance with the rest of the star, it keeps heating up. The hydrogen shell burns even faster, and the star shines more brightly as it climbs toward the very tip of the red giant branch. Stars with degenerate helium cores all reach this tip with roughly the same brightness and mass. Heavier stars, however, can get hot enough to start fusing helium before reaching the tip. For stars with helium cores between about 6/10 and 2 times the mass of the Sun, a spectacular event called a helium flash takes place. In stars with degenerate cores, this flash is incredibly powerful and happens fast over just a few days. The energy released is staggering, about 100 million times the brightness of the Sun. For a brief moment, it can even spike up to 100 billion times the Sun's brightness, equivalent to the light from the entire Milky Way galaxy. But strangely, this burst doesn't reach the surface. All that energy is spent on expanding and stabilizing the tightly packed core, so we don't see any fireworks from the outside. Once the core expands and cools down, the hydrogen burning slows and the star shrinks a little. Though it doesn't return to its original size, it enters a new calm stage and moves to the horizontal branch on the Hertzsprung-Russell diagram. The star's outer layers shrink, but its surface becomes hotter. Stars that go through a helium flash settle at the cooler end of the horizontal branch and shine as red clump stars, not as bright as red giants, but warmer. More massive stars with bigger helium cores sit farther along the branch, becoming hotter and sometimes unstable. These unstable stars can start to pulse, growing and shrinking in size over time. Some of them become RR Lyrae variables which blink rhythmically. Others may grow even hotter and appear in regions of the diagram known as the blue tail or blue hook. The exact shape and spread of the horizontal branch in a star cluster depends on many things, like the star's chemical makeup, how old it is, and how much helium it started with. Scientists are still piecing together all the details using computer models and observations. Even when a star finishes burning helium in its core, it doesn't die right away. Instead, it starts burning both helium and hydrogen in thin layers, or shells, that surround a dense core made mostly of carbon and oxygen. This final stage is called the asymptotic giant branch, and it looks a lot like the earlier red giant stage, but this time it's even more intense. Fusion happens faster, so this phase doesn't last very long. Now most of the energy comes from hydrogen burning in the outer shell, while the newly formed helium from this process sinks inward. From time to time, the helium-burning shell suddenly flares up in a thermal pulse, a powerful burst of energy. These thermal pulses usually happen in the later parts of this phase, but sometimes they can continue even after the star has technically left the asymptotic giant branch. Depending on how massive the star is and how rich it is in heavy elements, there might be just a few thermal pulses, or hundreds. As the star ages through this phase, it develops a wide zone of hot, swirling gas deep inside. This turbulence acts like an elevator, lifting material from the core up to the surface. This process is called a dredge-up. The second dredge-up brings inner materials upward, and sometimes it's followed by a third dredge-up. These events can pull carbon up from the core and spread it across the star's surface, turning it into a carbon star, a cool, reddish star that glows with strong carbon features. But it's not always that simple. In some cases, a process called hot bottom burning kicks in. This burns the carbon into oxygen and nitrogen before it reaches the surface. So there's a kind of tug of war going on. Some forces are trying to bring carbon up, while others are burning it away. This struggle shapes how bright and colourful the star becomes, especially in older star clusters. One fascinating type of star on the asymptotic giant branch is the Mira variable. These stars grow and shrink in regular cycles, with each pulse lasting anywhere from a few dozen to several hundred days. Their brightness can change by a huge amount, sometimes by a factor of 10,000, though the total energy they release doesn't change that much. The bigger and more massive these stars are, the longer they take to pulse, and the brighter they become. Because they shed their outer layers quickly, they release huge amounts of gas and dust into space. This makes them hard to see in normal light, but they glow brightly in the infrared. Many even give off special radio waves from molecules in their outer shells. This is known as OH maser activity. These stars are rich in oxygen, unlike carbon stars, but both types are created through the same kind of dredge-up processes. They are among the most beautiful and mysterious stars in the sky, changing, glowing, and releasing the very building blocks that may one day help form new stars, planets, or even life. Eventually, stars of medium weight reach the very top of the asymptotic giant branch. At this point, they've used up the fuel needed to keep burning their outer shells. Because they aren't heavy enough to start fusing carbon in the core, they begin to shrink and go through a phase known as the post-asymptotic giant branch superwind. During this time, they blow off their outer layers in a huge wind, creating a glowing cloud of gas and dust called a planetary nebula. In the centre of this nebula is an extremely hot core, the leftover heart of the star, which eventually cools down to become a white dwarf. The material that the star throws into space is full of heavy elements that were made inside the star. Depending on the type of star, the thrown-out gas might be full of oxygen or carbon. This gas forms a growing shell called a circumstellar envelope that gets cooler as it moves farther away from the star. In these cooler areas, dust and complex molecules begin to form. Because of the strong infrared light from the central star, the conditions in the envelope become perfect for master emission, producing bright, focused radio signals from certain molecules. Interestingly, even after a star has entered the post-asymptotic giant branch stage, it can sometimes go through new thermal bursts. These create rare and mysterious stars called born-again asymptotic giant branch stars. These strange stars can take many forms. Now let's look at more massive stars. In these stars, the core is already so large when the hydrogen shell starts burning that helium fusion begins before the core can be held up by electron degeneracy pressure. So when they expand and cool, they don't get brighter like smaller stars, but they were already very bright while still on the main sequence. These stars grow into huge and incredibly bright supergiants. Eventually their cores become so heavy that even electron degeneracy can't stop them from collapsing. When this happens, they end their lives either as a neutron star or a black hole. Some very massive stars, those with more than about 40 times the weight of the Sun, burn so brightly that their strong light blows away their outer layers in strong stellar winds. Because they lose their outer parts this way, they never become red supergiants. Instead, they stay very hot with a bluish-white colour throughout their lives. The most massive stars we see today have between 100 and 150 times the Sun's weight. If they were any bigger, their outer layers would be completely blown away by their own radiation. However, some smaller stars can also avoid becoming red giants if they are part of a close pair, where a nearby companion star pulls away their outer layers, or if they spin very fast. Fast spinning causes strong mixing, so the star doesn't form a separate core and outer layer. As a massive star gets older, the core, no longer full of hydrogen, gets hotter and denser as it is fed by the surrounding hydrogen-burning layers. In the most massive stars, the core gets hot enough to fuse carbon into even heavier elements like neon, sodium and magnesium through something called the alpha process. At the end of helium fusion, the core is mostly made up of carbon and oxygen. In stars heavier than about 8 times the weight of the Sun, this carbon lights up and fuses further. But stars just under this weight may only partly fuse carbon before being held up by electron degeneracy pressure. These stars eventually become white dwarfs made of oxygen, neon and magnesium. The exact weight limit for full carbon fusion depends on things like how many heavy elements the star started with, its metallicity, and how much weight it lost during its asymptotic giant branch phase. But in general, full carbon burning begins in stars with around 8 to 9 times the Sun's weight. After the carbon is used up, the core reaches around 2.5 times the Sun's weight and gets hot enough to begin fusing even heavier elements. But before oxygen starts fusing, the neon starts capturing electrons, starting a process called neon burning. In stars between about 8 and 12 times the weight of the Sun, this can lead to a runaway reaction and end in a strong explosion called an electron capture supernova. In even heavier stars, neon fusion happens more calmly. This is followed by the burning of oxygen and then silicon, until the core becomes filled with iron-like elements, which are the final products of fusion. Around this iron core, shells of lighter elements keep burning, but the last stage happens quickly. Once the core has finished turning carbon into iron, it only takes a few hundred years for everything to fall apart. During this time, the outer parts of the star hardly have time to react, so the star still looks normal on the outside. Eventually, the iron core reaches what's called the effective Chandrasekhar limit, the highest weight it can handle before collapsing. This limit is a bit higher than the original Chandrasekhar limit because of different effects like relativity, heat, and pressure from the outer layers. For red supergiants, the effective limit is around 1.34 times the Sun's weight, but in more massive stars, it can be over 1.8 times the Sun's weight. Once the iron core hits this limit, it starts collapsing quickly. Electrons are absorbed by iron nuclei, and the star's core can no longer hold itself up. What follows is an amazing end, a supernova explosion, or in the case of even more massive stars, a direct collapse into a black hole. When a very massive star reaches the end of its life, something dramatic happens at its core. After using up all its nuclear fuel, the core can no longer hold up the huge weight of the star pressing down on it. So, the core falls in under gravity's pull. This collapse leads to one of two results. If the falling core is not too heavy, it becomes an incredibly dense object called a neutron star. But if the core's weight is more than a certain limit, known as the Tolman-Oppenheimer-Volkoff limit, then even neutron pressure cannot stop the collapse, and a black hole forms instead. During this sudden collapse, a huge amount of energy is released. Scientists still do not fully understand how this energy behaves, but we do know that part of it creates a huge explosion known as a supernova. Depending on the shape of the star and what elements are in its outer layers, this explosion might be a Type 1b, Type 1c, or Type 2 supernova. One of the most mysterious and powerful parts of this process is the release of neutrinos, tiny, almost weightless particles that hardly interact with anything. When the core falls in, a huge flood of neutrinos rushes outward. This was directly seen in the well-known supernova called SN 1987A, which exploded in the year 1987. These neutrinos don't just fly away. Some of them interact with the star's material. They can break atoms apart, knock free neutrons and protons, and pass heat and motion into the nearby layers of the star. All of this helps create the supernova's huge shock wave, the wave that blasts the outer parts of the star into space. In the densest parts of the falling matter, electrons are sometimes forced to combine with protons, making even more neutrons. As the shock wave bounces back, it hits nearby material, bombarding it with these loose neutrons. Some of the atomic cores catch these neutrons, leading to the creation of heavy elements even heavier than iron, and including radioactive ones, possibly all the way up to and beyond uranium. Now, it is true that older, non-exploding stars, especially red giants, can also make some heavy elements using neutrons released in slower side reactions. But the kinds and amounts of heavy elements made in red giants are quite different from those made during a supernova explosion, and interestingly, neither kind of process alone can explain all the heavy elements we find in our solar system today. That's why scientists believe that supernovae, crashes between neutron stars, and mass loss from red giants all help make and spread these heavier elements across the universe. The energy released during the core's fall not only makes heavy elements, but also throws them outward at amazing speeds, much faster than the speed needed to escape the star. This is what powers the incredible brightness and strength of a Type 1b, Type 1c, or Type 2 supernova. However, even today, scientists are not completely sure how enough energy moves from the falling core to the rest of the star to cause such a powerful explosion. Computer models can explain part of it, but not all. One hopeful idea involves neutrino oscillations, the way neutrinos change types as they move through space. These changes may help move more energy, both by changing the total energy in each kind of neutrino and through strange effects predicted by Einstein's theory of general relativity. Some interesting clues come from binary neutron stars, pairs where two neutron stars circle each other. These systems must have come from two different supernovae, and the way they act gives us hints about the differences between various kinds of supernova explosions. In particular, if a star's core is mostly made of oxygen, neon, and magnesium, the supernova it creates may be clearly different from one coming from a core made mostly of iron, even if they explode with about the same strength. Among the most extreme cases are the biggest stars in the universe. The heavier stars known today can sometimes be totally destroyed in an especially strong kind of supernova caused by something called pair instability. In this rare type of explosion, the energy released is greater than the gravity holding the star together, so the whole star is blown apart, leaving behind no black hole at all. Even heavier stars that lived billions of years ago were so big that, instead of exploding, they fell instantly into black holes because of a process called photodisintegration, where their intense heat broke apart atomic cores and caused total collapse. After a star dies and uses up its fuel, what's left depends on how heavy it was during its life. A star with a weight similar to our Sun, about 1 solar mass, will shrink into a white dwarf, a very dense object with a weight of about 0.6 solar masses, packed into a space no bigger than the Earth. White dwarfs stay stable because the gravity pulling inward is balanced by a special kind of pressure that comes from electrons being squeezed together. This is called electron degeneracy pressure, which comes from the Pauli exclusion rule, a rule in quantum physics that says two electrons cannot be in the same state at the same time. Interestingly, white dwarfs act in a strange way. The heavier they are, the smaller they become. Once they form, white dwarfs don't burn any more fuel, they simply shine by letting out leftover heat into space. This cooling takes billions of years. When a white dwarf is newly formed, it is extremely hot. Its surface can be hotter than 100,000 Kelvin, and its core is even hotter. In its first 10 million years, a lot of its energy is lost through the release of neutrinos. After about 1 billion years, most of its heat has been given off, and it keeps getting cooler. The makeup of a white dwarf depends on how heavy the original star was. A star with a weight between about 8 and 12 times the Sun's weight will go through a phase where it burns carbon into elements like magnesium, neon, and small amounts of others. If such a star loses enough of its weight before collapsing, it can leave behind a white dwarf made mostly of oxygen, neon, and magnesium, as long as the carbon burning is not too violent to cause a supernova. Stars that have about the same mass as our Sun don't get hot enough inside to start burning carbon. Once they've burned through their hydrogen and helium fuel, they can't move on to the next stage of fusion. Instead, they shrink and settle down as white dwarfs, which are small, very dense stars mostly made of carbon and oxygen. These white dwarfs don't collapse under their own weight because they aren't heavy enough, unless more material gets added to them somehow later on. Now, if a star is much smaller, less than half the mass of our Sun, it won't even be able to start helium fusion. These tiny stars live for a very, very long time, but when they finally run out of fuel, they become white dwarfs too. However, these smaller white dwarfs are made mostly of helium instead of carbon and oxygen. Over an incredibly long time, far longer than the current age of the universe, white dwarfs cool down. Eventually they stop glowing and become completely dark, cold objects called black dwarfs. But the universe is still too young for that to have happened yet. The universe is currently less than 14 billion years old, so no black dwarfs exist yet. Sometimes, a white dwarf collects extra mass. This can happen in two ways. Either it merges with another star, or it pulls in matter from a nearby star that's orbiting close to it. If it keeps gaining mass and becomes heavier than a certain limit, called the Chandrasekhar limit, which is about 1.4 times the mass of the Sun, then a dramatic change occurs. The pressure from electrons, which usually holds up the star, is no longer enough to stop the collapse. What happens next depends on what the white dwarf is made of and how hot its core is. In some cases, it collapses into an even denser object called a neutron star. In others, the carbon and oxygen inside ignite in a runaway chain reaction, setting off a huge explosion known as a Type 1a supernova. These Type 1a supernovae are brighter than the more common Type 2 supernovae, which happen when massive stars die, even though they release less total energy. After crossing the Chandrasekhar limit, no white dwarf can survive, unless it is spinning very, very fast. In that case, the spinning motion creates a centrifugal force that helps hold it together just a little longer. In some close binary star systems, the white dwarf pulls hydrogen gas from its larger companion star. This gas piles up around the white dwarf until it becomes hot enough for nuclear fusion. Suddenly the hydrogen ignites in a powerful burst of energy called a nova. Unlike a supernova, a nova doesn't destroy the white dwarf. It survives, and may go through this process again and again. To understand how all of this works, we need to take a closer look at atoms, the tiny building blocks of everything. Atoms are mostly empty space. The core, or nucleus, is very small and extremely dense. Surrounding the nucleus is a cloud of electrons moving very fast. To grasp how tiny the nucleus is, think of an atom the size of a football stadium. In that case, the nucleus would only be about the size of a speck of dust floating in the air. But when a massive star dies, something extraordinary happens. Its core collapses under its own enormous gravity. The pressure becomes so intense that electrons and protons inside atoms are forced to combine in a process called electron capture, creating neutrons. Without electrons to help keep atoms apart, the core becomes one giant mass of neutrons, squashed tightly together like a single gigantic atomic nucleus. What remains is called a neutron star, an incredibly small but unbelievably dense object. A neutron star is only about 10 kilometers wide, roughly the size of a large city, yet it contains more mass than the Sun. Just 1 teaspoon of a neutron star matter would weigh more than a mountain on Earth. The reason a neutron star doesn't collapse even further is because of a special quantum law called the Pauli exclusion principle. This law says no two neutrons can be in the same exact state, and that resistance holds up the neutron star, similar to how electron pressure supports a white dwarf, but much stronger. And there's more. As the core of the dying star collapses into a neutron star, it starts to spin faster and faster, like an ice skater pulling in their arms. This is due to a physics rule called the conservation of angular momentum. Some neutron stars spin at mind-blowing speeds, hundreds of times every second. The fastest ones complete a spin in just 1.5 thousandths of a second, meaning they spin over 600 times per second. Some spinning neutron stars have strong magnetic fields, and their magnetic poles sweep across space like a lighthouse beam. Each time this beam points toward Earth, we see a pulse of energy, usually as radio waves. These objects are called pulsars. Some pulsars don't just emit radio waves, they also give off visible light, X-rays, or even gamma rays. But sometimes a collapsing star's core doesn't stop at the neutron star stage. If the leftover mass is greater than about 2 to 3 times the mass of the Sun, though the exact number is still not fully known, even neutron pressure can't hold it up. The core collapses endlessly and forms a black hole. A black hole is an object with gravity so strong that not even light can escape from it. According to Einstein's theory of general relativity, once anything crosses the event horizon, the invisible boundary around a black hole, it's lost forever. No light, no matter. Not even information can come back out. However, some new ideas in quantum physics suggest that a tiny bit of information might somehow escape. Black holes aren't just theories, they are supported by real observations. Astronomers have seen stars orbiting invisible objects, measured gravitational waves from black hole collisions, and detected bright X-rays from hot gas falling into them. Still, many mysteries remain. Scientists don't yet fully understand how a core collapse supernova works, the powerful explosion that often happens when a massive star dies. It's unclear whether some stars collapse directly into black holes without exploding, or whether they first form unstable neutron stars that later collapse into black holes. It's also still uncertain how a star's original mass and elements decide whether it ends up as a white dwarf, neutron star, or black hole. To uncover these secrets, astronomers need to study many more supernovae and the leftovers they leave behind. To help with this, scientists use special tools called stellar evolutionary models. These are advanced computer simulations that track how a star changes over time, from birth to death. The models start with a star's mass and chemical makeup, then use physics laws, like the balance of forces inside a star, to figure out how it will behave. The models show how a star's brightness and surface temperature change throughout its life. They also let scientists track where a star is on something called the Hertzsprung-Russell diagram, a special chart used to follow a star's life stages. By comparing real stars to these models, astronomers can estimate how old a star is and what might happen to it in the future. These tools help scientists piece together the grand story of how stars live, die, and what remains after they're gone. High up in the night sky, in the famous constellation called Orion, lies a truly remarkable star, Betelgeuse. This star is not just big, it's enormous, glowing with a deep, fiery red light that makes it one of the most eye-catching stars in the heavens. Among all the stars visible to the naked eye, Betelgeuse usually ranks as the 10th brightest. Within Orion itself, only the dazzling blue-white star Rigel outshines it. One of the most fascinating things about Betelgeuse is that its brightness changes over time. It doesn't shine with a steady light like many other stars. Instead, it's what astronomers call a semi-regular variable star. That means its light grows stronger and weaker in a repeating pattern. Over the course of about 400 days, Betelgeuse's brightness goes up and down between a magnitude of 0.0 and 1.6. No other bright star we see in the sky shows such a wide range in brightness. In fact, if you could see in near-infrared light, Betelgeuse would appear even more brilliant than any other star in the sky. The star's official name in the language of science is Alpha Orionis. This naming comes from a system invented by the German astronomer Johann Bayer in the early 17th century. Scientists often shorten the name to Alpha Ori for convenience. Now, let's talk about just how huge Betelgeuse really is. This star is an absolute monster. Its radius is estimated to be somewhere between 640 and 764 times greater than that of our Sun. If we could magically move Betelgeuse to the centre of our solar system, it would stretch far past the orbit of Mars. In fact, it would swallow up Mercury, Venus, Earth, and Mars, and its outer layers would reach beyond the asteroid belt. Even though its size is gigantic, Betelgeuse isn't the heaviest star out there. Most astronomers believe it has a mass that falls somewhere between just under 10 and a little over 20 times that of the Sun. Despite being relatively close in the grand scale of the universe, we still don't know exactly how far away it is. The best estimates suggest a distance between 400 and 600 light-years from Earth. A pretty large range for such a nearby star. In terms of how much light it gives off overall, what astronomers call absolute magnitude, Betelgeuse shines with a magnitude of about -6. That makes it exceptionally bright, even though it's not among the oldest stars. In fact, Betelgeuse is young by stellar standards, probably less than 10 million years old. But because it's so massive, it burns through its fuel at an incredible pace, and lives a much shorter life than smaller stars like the Sun. Astronomers believe Betelgeuse is heading toward a spectacular end. Within the next 100,000 years, it is expected to explode in a powerful event called a supernova. When that happens, the star will shine as brightly as the half moon, lighting up our night sky for more than 3 months. Don't worry though, this dramatic explosion, while stunning to witness, won't harm life on Earth. Interestingly, Betelgeuse hasn't always been in its current position. Long ago, it was part of a group of young hot stars known as the Orion OB1 Association. This group includes the stars that form Orion's belt. At some point in its past, Betelgeuse was flung out of this cluster and became what scientists call a runaway star. It is now zooming through space at a speed of about 30 kilometers per second. That's fast enough to create a bow shock, a wave of gas and dust like the waves that form in front of a speeding boat, that stretches more than 4 light years wide. Back in the year 1920, Betelgeuse became the first star outside our solar system to have its visible surface, or photosphere, measured directly. Since then, astronomers have learned that Betelgeuse is not perfectly round. Its apparent size in the sky, called angular diameter, changes between 0.042 and 0.056 arc-seconds. This variation happens because of its uneven shape, darkening near the edges, constant pulsations, and the way its appearance shifts in different types of light. Surrounding this red supergiant is a huge, uneven cloud of gas and dust, more than 250 times larger than the star itself. This cloud was formed as Betelgeuse began to shed its outer layers into space. When it comes to how big a star looks in the sky, only the Sun and another red giant named R Doradus appear larger than Betelgeuse in terms of angular size. A mysterious and exciting event took place starting in October of the year 2019. Betelgeuse suddenly began to dim, and by February of the year 2020, it had become 3 times dimmer than usual. Its brightness dropped from magnitude 0.5 to around 1.7. Then, just as mysteriously, it began to brighten again. By April of the year 2023, Betelgeuse had returned to its normal brilliance, reaching a peak of magnitude 0.0. Interestingly, data from infrared telescopes collected over the past 50 years showed no major change in Betelgeuse's total energy. This told astronomers that the star itself wasn't getting weaker. Instead, something must have blocked its light. Later observations using the Hubble Space Telescope suggested that Betelgeuse had ejected a large cloud of material from its surface. That material travelled millions of miles, cooled down and turned into a dust cloud, which temporarily dimmed the star's light from our point of view. The star's striking reddish glow has fascinated people for thousands of years. The ancient Greek astronomer Ptolemy described its colour using the word hypokeiros, which meant something like orangey red. Later translations into Latin called it rubedo, meaning ruddiness. Interestingly, Chinese astronomers who made observations 3 centuries before Ptolemy described Betelgeuse as yellow, not red. If their records were accurate, it might mean that Betelgeuse passed through a yellow supergiant phase, which modern scientists now believe is possible. In southern Australia, Aboriginal peoples have told stories passed down through generations that describe how Betelgeuse's brightness changes. This shows that even ancient skywatchers noticed its unpredictable nature. In more recent times, Betelgeuse's changing light has also been recorded. In the year 1836, the English astronomer Sir John Herschel began studying Betelgeuse's brightness in his book Outlines of Astronomy. Between the years 1836 and 1840, he noticed dramatic changes in how bright the star appeared. In October of 1837, and again in November of 1839, Betelgeuse even shined brighter than Rigel. After about 10 quiet years, Herschel observed another brightening event that peaked in the year 1852. Observations in the 20th century continued to record these shifts in brightness. For example, the American Association of Variable Star Observers noted that Betelgeuse reached a maximum brightness of magnitude 0.2 in the years 1933 and 1942. It also dropped to a minimum of magnitude 1.2 in the years 1927 and 1941. Some experts believe this variability may be the reason why Johann Bayer, in his star atlas Uranometria, published in the year 1603, gave Betelgeuse the Alpha designation, suggesting it was sometimes brighter than Rigel, which holds the Beta label. Among the Inuit people of the Arctic, Betelgeuse was also thought to outshine Rigel, partly because it appears higher in their sky and glows with a stronger red hue. They named it Luridjuak, meaning large star. The very first time anyone actually measured the size of Betelgeuse was in the year 1920. This important step was made by two scientists named Albert Michelson and Francis Pease, with support from John Anderson. They used a special tool called a 6-meter interferometer, which they attached to a 2.5-meter telescope at the Mount Wilson Observatory in California. With this setup, they were able to measure the star's angular diameter, basically how wide it looked in the sky, as 0.047 arc-seconds. Using a parallax, a way to measure distance using angles, of 0.018 arc-seconds, they figured out that Betelgeuse had a real diameter of about 384 million kilometers. That's about 2.5 times the distance from the Earth to the Sun. However, this early measurement wasn't perfect. There were many challenges, such as something called limb darkening, where the edges of a star looked dimmer than the center, and other effects that made it hard to get a completely accurate result. In the 1950s and 1960s, two big breakthroughs helped astronomers learn even more about Betelgeuse and stars like it. The first was the Stratoscope Balloon Project, which sent telescopes high into the Earth's atmosphere on giant balloons. These high-flying telescopes took very detailed pictures of the Sun's surface, helping scientists understand how stars behave. The second breakthrough was a powerful book published in the year 1958 called Structure and Evolution of the Stars. It was written by two astronomers from Princeton University, Martin Schwarzschild and Richard Herm. This book introduced the use of computers to model how stars live and change over time. Thanks to these models, scientists confirmed that stars like Betelgeuse have convective layers, outer parts that churn and bubble like boiling water. By the 1970s, the way astronomers observed stars had improved a lot. A French astronomer named Antoine Laberie came up with a clever technique called speckle interferometry. This method helped to reduce the blurriness caused by Earth's moving atmosphere. Before this, the turbulence in our air always made it difficult to get sharp pictures of stars. Thanks to Laberie's technique, ground-based telescopes suddenly had a much clearer view. For the first time, scientists could study the outer surface of Betelgeuse, called the photosphere, in fine detail. During this same period, astronomers also upgraded infrared telescopes placed on high mountain peaks, such as Mount Wilson in California, Mount Locke in Texas, and Mauna Kea in Hawaii. These infrared tools allowed them to peer through the dusty clouds that surround Betelgeuse. These clouds, called circumstellar shells, appeared to hold huge bubbles of gas. Many believed these were created by strong convection currents inside the star, where hot gas rises to the surface and cooler gas sinks down again. But even more exciting discoveries came during the late 1980s and early 1990s. Astronomers started using a new method called aperture masking interferometry. This involved putting a mask with tiny holes over a telescope's main mirror. The mask turned the telescope into a type of interferometer, which could combine light from different angles to produce incredibly sharp images. A team led by J.E. Baldwin at the Cavendish Astrophysics Group used this method to make some of the most accurate measurements of Betelgeuse's surface ever recorded. They even found bright spots, hotter areas on the surface of the star that glowed more than their surroundings. These were the very first visible and infrared images ever taken of the surface of a star other than our Sun. They were captured using ground-based telescopes like the COAST interferometer, and those bright patches matched what Martin Schwarzschild had predicted decades earlier: giant convective cells bubbling on the surface of red supergiants like Betelgeuse. Then came the year 1995, when the Hubble Space Telescope took things to a whole new level. Using its faint object camera, Hubble captured an ultraviolet image of Betelgeuse that was sharper than anything ever seen from the ground. Earth's atmosphere blocks most ultraviolet light, so this kind of image could only be taken from space. In this Hubble photo, scientists spotted a bright region in the southwest part of the star. This spot was about 2000 degrees Kelvin hotter than the rest of the surface. Later on, Hubble's Goddard high-resolution spectrograph suggested that this hotspot might actually be one of Betelgeuse's rotational poles. From that, astronomers figured out that the star's axis is tilted about 20 degrees as seen from Earth, and the position angle is around 55 degrees from celestial north. By December of the year 2000, scientists measured Betelgeuse's size again using the Infrared Spatial Interferometer, ISI. This time, they found the angular diameter to be about 55.2 milliseconds, which was very close to the value measured by Michelson nearly 80 years earlier. At the same time, the Hipparcos mission estimated Betelgeuse's parallax at around 7.63 milliseconds, which suggested that the star's radius was about 3.6 astronomical units. That's more than 3 times the distance between the Earth and the Sun. But then came a surprise. In the year 2009, another study revealed that Betelgeuse had shrunk by about 15% since 1993, and it seemed to be shrinking faster and faster. Oddly though, its brightness hadn't changed much. This made scientists wonder if the shrinking was even real. Maybe it was just caused by layers of gas moving around in the star's outer atmosphere. Astronomers also became very interested in the complex outer parts of Betelgeuse. As a red supergiant, it's one of the most important types of stars in the galaxy. Stars like it lose a lot of matter, and this material floats into space and helps form new stars and planets. But scientists still don't fully understand how this mass loss happens. Thanks to better images, they started to get closer to an answer. In July of the year 2009, the European Southern Observatory released stunning images from the Very Large Telescope Interferometer. These images showed a massive plume of gas stretching 30 astronomical units away from Betelgeuse, about as far as the planet Neptune is from the Sun. This wasn't just a one-time event. Astronomers have found at least 6 separate layers of gas surrounding the star. Figuring out why Betelgeuse is shedding so much material could help explain how these stars eventually end their lives in gigantic explosions called supernovae. Betelgeuse is also known as a pulsating semi-regular variable star. That means its brightness changes in cycles because its size and temperature are constantly shifting. In one study, scientists Richard Wassertonic, Edward Guinan, and Thomas Calderwood saw a deep dimming of the star and suggested it was caused by a rare overlap of 2 cycles, one lasting 5.9 years and another lasting 425 days. By late 2019, other astronomers began to wonder if something else was dimming the star, like a huge outburst of gas or a thick cloud of dust. Then, in early 2020, the Hubble Space Telescope found signs that Betelgeuse had indeed blasted out a huge amount of hot material. This material cooled and turned into a cloud of dust that blocked part of the star's light, covering about 1/4 of its surface. Hubble had tracked this material during September, October and November of 2019. By December, and in the early months of 2020, many other telescopes confirmed that Betelgeuse was much dimmer than normal. By January of 2020, the star's brightness had dropped by a factor of about 2.5, going from magnitude 0.5 to 1.5. In February, it reached its faintest point in 25 years, at magnitude plus 1.614, which made it dimmer than the star Aldebaran and knocked it out of the top 10 brightest stars in the sky. This led to rumours everywhere that Betelgeuse might soon explode as a supernova. But scientists quickly reminded everyone that this explosion probably wouldn't happen for another 100,000 years. By mid-February of 2020, Betelgeuse stopped fading and even started to brighten again. On February 22nd, the dimming seemed to end. Just 2 days later, scientists checked and saw no big changes in the star's infrared emissions over the past 50 years, suggesting the dimming wasn't caused by anything happening deep inside the star. Instead, astronomers now believe the dimming was probably caused by large dust grains forming near the star, possibly after a previous gas outburst. Some also think huge star spots, cooler, darker patches on the star's surface, might have helped cause the dimming. Then, on March 31st, astronomers reported that Betelgeuse had started brightening very quickly. Between the months of May and August each year, Betelgeuse becomes very difficult to see from Earth. That's because it appears too close to the Sun in the sky, making its glow invisible to the naked eye during this time. In the year 2020, just before it passed behind the Sun, in what astronomers call a conjunction, Betelgeuse had grown brighter, reaching a visual brightness, or magnitude, of plus 0.4. But then, something unexpected happened. In June and July of that same year, a spacecraft called Stereo A picked up signs of the star dimming again, this time by about 0.5 magnitudes. This fading caught scientists off guard. They had expected Betelgeuse to brighten again around August or September, but the early dimming hinted that another drop in brightness might happen sooner than expected. Sure enough, on the 30th of August in the year 2020, astronomers detected something strange. They noticed a second cloud of dust being released from Betelgeuse, which seemed to be linked to a smaller dimming event that had happened earlier in the month, on the 3rd of August. By the time June of the following year rolled around, June of 2021, scientists began to think this dust might have formed because a cool spot had appeared on the surface of Betelgeuse. Later that August, another research group confirmed this idea. Then, in August of 2022, the Hubble Space Telescope offered even stronger evidence. It suggested that the dust likely came from a massive surface explosion called a surface mass ejection. These are like solar flares on the Sun, but far more intense. Astronomers also found that the dimming may have happened because two different cycles overlapped. One of these cycles lasted 416 days, while the other stretched across 2010 days. When these two cycles lined up just right, they created what scientists call a grand minimum, a very deep and noticeable low point in the star's brightness. This idea wasn't new. It had first been proposed many decades ago by the astronomer L. Goldberg. Then came some good news. In April of the year 2023, astronomers announced that Betelgeuse had returned to its peak brightness. It had reached a visual magnitude of 0.0, making it once again one of the brightest stars in the sky. In the V-band, a part of the light spectrum astronomers often use, it was recorded at 0.1 magnitude. Thanks to its deep orange-red colour and its eye-catching position in the famous constellation Orion, Betelgeuse is one of the easiest stars to spot with the naked eye. Even people who don't know much about the night sky can usually find it without needing a telescope. Betelgeuse forms one corner of the Winter Triangle, a group of 3 bright stars that help stargazers find their way through the cold season sky. It's also part of another large star pattern known as the Winter Hexagon, which links together many of the brightest stars visible during the winter months. Each year, in early January, Betelgeuse rises in the eastern sky just after sunset. This marks the beginning of its best viewing season. From around the middle of September to the middle of March, the star shines brilliantly and can be seen from nearly every inhabited part of Earth. The best time to see it is in the middle of December. The only exception is in the very southern part of Antarctica, south of 82 degrees latitude, where it never rises high enough above the horizon. By the month of May in the northern hemisphere, and by June in the southern hemisphere, Betelgeuse starts to sink low in the western sky. It becomes visible only for a short time after sunset before it disappears. A few months later it returns, this time on the eastern horizon, shortly before the sun rises. However, in the weeks in between, especially in June and July, Betelgeuse becomes completely invisible to the naked eye. During this period, it can only be observed with special telescopes during daylight hours. Interestingly, in Antarctica, between 70 and 80 degrees south latitude, the star might still be seen faintly in the northern sky, around noon twilight during the long polar night, when the sun never rises. Betelgeuse is a variable star. This means that its brightness changes over time. Its visual brightness, or magnitude, can range from 0.0 at its brightest to about plus 1.6 when it's dimmer. Sometimes Betelgeuse even shines brighter than the nearby blue-white star Rigel, becoming the 6th brightest star in the night sky. On rare occasions, it can even outshine Capella, but when it dims to its lowest levels, it drops below stars like Deneb and Beta Crucis, and can fall all the way down to being only the 20th brightest star in the sky. Astronomers have also discovered that Betelgeuse has up to 9 very faint companion stars nearby. These stars appear close to Betelgeuse in the sky, lying between 1 and 4 arc-minutes away. But they are all much dimmer than magnitude 10, which means you would need a strong telescope to see them. To figure out how far away stars like Betelgeuse are from Earth, astronomers use a method called parallax. This involves measuring how a star appears to shift slightly in the sky when observed from 2 different points in Earth's orbit, 6 months apart. Even though the shift is tiny, often just a small fraction of an arcsecond, it can help scientists calculate how far the star is. The first time this method worked was in the year 1838, when the astronomer Friedrich Bessel successfully measured the parallax of a star. Ever since then, astronomers have tried to figure out how far away Betelgeuse is, but it has proven to be surprisingly difficult. Knowing the exact distance is very important because it helps us calculate how bright Betelgeuse really is, how big it is, how hot it gets, how old it might be, and how much mass it holds. Back in the year 1920, when astronomers first used a technique called interferometry to measure Betelgeuse's size, they thought its parallax was 0.018 arcseconds. That would have placed it about 56 parsecs away, or roughly 180 light years, but this turned out to be way too close, which threw off all the other calculations, like its size and brightness. Over the next few decades, scientists came up with all kinds of estimates for Betelgeuse's distance. Some guesses were as high as 400 parsecs, which equals around 1,300 light years. Before the Hipparcos star catalogue was released in the year 1997, two different measurements had already created some confusion. One estimate from the year 1991 gave a parallax of 9.8 milliseconds, placing Betelgeuse at about 102 parsecs, or 330 light-years away. Another estimate from 1993, based on early Hipparcos data, suggested a parallax of 5 milliseconds, meaning a distance of around 200 parsecs, or 650 light-years. Because these measurements didn't agree, astronomers had to work with a wide range of possible distances, which led to big differences in estimates of Betelgeuse's true size, temperature, and brightness. When the full Hipparcos data came out in 1997, it showed a parallax of 7.63 milliseconds, which suggested a distance of 131 parsecs, or 427 light-years. This seemed more reliable, with a smaller margin of error. However, later studies showed that the errors for stars like Betelgeuse, which change in brightness, had been underestimated. In the year 2007, scientists used better tools and got a more precise measurement, 6.55 milliseconds. This suggested that Betelgeuse was about 152 parsecs away, or roughly 500 light-years, with a possible error of plus or minus 65 light-years. Then, in 2008, scientists used radio telescopes in the Very Large Array and found a parallax of 5.07 milliseconds. That meant Betelgeuse could be around 197 parsecs away, about 643 light-years. But again, there was some uncertainty. The lead researcher, Edward Harper, explained that the Hipparcos data was helpful but still had unknown errors, so his team combined both the optical and radio data to try to cancel out the mistakes and get a better estimate. Later observations from telescopes like ALMA and E. Merlin improved things even more. These showed a parallax of 4.51 milliseconds, meaning Betelgeuse might be as far as 222 parsecs away, around 724 light-years. In the year 2020, data from an instrument called the Solar Mass Ejection Imager, on board the Coriolis satellite, was used along with 3 advanced modelling techniques. This gave a refined parallax of 5.95 milliseconds, which meant Betelgeuse was likely about 168 parsecs away, or roughly 548 light-years. Based on this updated distance, astronomers realised that Betelgeuse was about 25% smaller and about 25% closer to Earth than they had previously believed. In the year 2022, a group of scientists made a surprising discovery about Betelgeuse, a massive and mysterious red star that has fascinated astronomers for centuries. According to their new study, Betelgeuse might actually be smaller and much closer to Earth than everyone had thought before. Their findings were partly based on ancient sky-watching records from about 1,000 years ago. These old writings describe Betelgeuse as having a yellowish colour, not the deep red we see today. That change in colour tells astronomers a lot about how the star has evolved over time. A redder colour means Betelgeuse has cooled down, expanded, and aged. Because of this change, researchers now believe that the star may not be as massive as earlier studies claimed. Instead of weighing more than 20 times the mass of our Sun, it might be closer to 14 times our Sun's mass, and that's not all. The same study suggested that Betelgeuse is not as far away as once believed. It might lie at a distance of around 125 parsecs from Earth, That's about 410 light-years. This new estimate actually agrees quite well with older measurements taken by the Hipparcos satellite. But getting an exact distance for Betelgeuse isn't easy. The European Space Agency's Gaia mission, which is designed to measure the positions and distances of stars with amazing accuracy, runs into trouble when dealing with extremely bright stars. Gaia's instruments can't handle stars that are brighter than about 6th magnitude. Since Betelgeuse is much brighter than that, it didn't appear in the mission's second data release in the year 2018, or even in the third release in the year 2022. Betelgeuse is what astronomers call a semi-regular variable star. That means it doesn't shine with a constant brightness. Instead, it grows brighter and dimmer over time, following cycles that can be predicted, but not always perfectly. Sometimes it pulses steadily, but other times its brightness changes in odd and unpredictable ways. It belongs to a special group of stars known as SRC stars, which are enormous red stars that slowly pulse and change brightness. These brightness changes can be as much as 1 full magnitude, and the cycles can last from just a few dozen days to several hundred. Most of the time, Betelgeuse glows at a brightness of around plus 0.5 magnitude. But it's a very moody star. It can shine as brightly as 0.0 magnitude or fade down to plus 1.6. Astronomers have listed Betelgeuse in the General Catalogue of Variable Stars and noted that it may follow a long-term cycle that lasts around 2,335 days. Other detailed studies found a main cycle of about 400 days, a shorter cycle of around 185 days, and a very long one of about 2,100 days. In February of the year 2020, during a mysterious dimming event, Betelgeuse was recorded at its faintest brightness ever in visible light, plus 1.614 magnitude. These changes in brightness are caused by the star's outer layers expanding and shrinking, almost like it's breathing. These rhythmic movements are called radial pulsations and are a natural part of a star's life. Some of the cycles, like the one that lasts around 185 days, are linked to what's called the first overtone, a particular way the star's layers move in and out. Astronomers can track these movements by observing the Doppler shift in the star's light, which shows whether the star's surface is moving toward or away from us. These shifts clearly show that Betelgeuse swells and contracts. However, changes in its temperature or in the colours of its light are harder to detect. Scientists have also been able to measure Betelgeuse's actual size as it changes over time. The 185-day cycle matches the pulsation of the first overtone. By comparing the shorter and longer cycles, astronomers can learn more about the star's internal structure and even estimate its age. But the really long cycle, the one that lasts over 2,000 days, doesn't match any simple explanation based on pulsation alone. When astronomers use high-powered instruments to look closely at Betelgeuse, they sometimes see bright spots on its surface. These are believed to be giant convection cells, huge areas where hot gas rises and cooler gas sinks, similar to boiling water in a pot. Each of these cells can be half the width of the entire star, and they may shine with 5 to 10% of the star's total light. Some scientists think the star's long, slow brightness cycle might be caused by these enormous cells, especially when their motion combines with the star's slow spin. Others think the cycle might be caused by the presence of a companion star, magnetic fields, or more complex non-radial pulsations, such as gravity waves, also known as G-modes. In addition to these regular changes, Betelgeuse also shows tiny, random flickers in brightness. These seem to come from granulation, which is a type of small-scale turbulence on the star's surface, similar to what we see on the Sun, but on a much grander scale. Way back on the 13th of December in the year 1920, Betelgeuse made history by becoming the first star beyond our solar system to have its size directly measured. The technology used, called interferometry, was brand new at the time, but it worked. By treating the star as a simple glowing disk, astronomers estimated its size to be about 0.047 arc-seconds across. After adjusting for something called limb darkening, the way the edges of the star look dimmer than the centre, the measurement increased to about 0.055 arc-seconds. Over the years, other measurements have ranged between 0.042 and 0.069 arc-seconds. When these angular sizes are matched with distance estimates ranging from 180 to 815 light-years, astronomers estimate that Betelgeuse's radius might fall anywhere between 1.2 and 8.9 astronomical units, or AU. For comparison, Mars orbits the Sun at about 1.5 AU, Ceres at 2.7 AU, and Jupiter at around 5.5 AU. So if Betelgeuse replaced our Sun, its surface could easily stretch past Jupiter's orbit, though it would still fall short of Saturn, which lies at about 9.5 AU. To describe the size of cool, bloated stars like Betelgeuse, scientists often use a special measurement called the Rossland radius. This refers to the distance from the centre of the star to the point where its visible light escapes freely into space. This value depends on the star's temperature and how much energy it gives off, but this number doesn't always match what's seen in direct measurements, because those depend on things like limb darkening and the wavelength of light being used. For example, a directly measured angular diameter of 55.6 milliseconds might correspond to a Rossland diameter of 56.2. If there's dust or gas around the star, the size might appear smaller, down to around 41.9 milliseconds. To solve all these measurement problems, astronomers have built powerful tools. The first idea for astronomical interferometry came from Hippolyte Fizeau in the year 1868. He suggested that using 2 openings instead of 1, like our eyes do to see depth, could help measure the sizes and shapes of stars. His idea led to the Michelson interferometer in the 1880s, which eventually helped scientists measure Betelgeuse. As time went on, the technology improved. By using multiple telescopes and combining the light through Fourier analysis, astronomers were able to create very detailed images of distant stars. In the 1990s, this allowed them to see the bright spots on Betelgeuse's surface. Other advancements included adaptive optics to reduce the blurring caused by Earth's atmosphere, space telescopes like Hipparcos, Hubble, and Spitzer, and advanced instruments like AMBER, which combines the light from 3 telescopes to produce incredibly sharp images at millisecond resolution. Different types of light reveal different things about Betelgeuse's size. In visible light, the star's atmosphere scatters light more so it appears larger. In the near-infrared, this scattering is less, revealing the true edge of the star's surface. In the mid-infrared, the glow from the star's warm outer layers makes it look larger again. In the year 1996, astronomers measured Betelgeuse's size as about 56.6 milliseconds. In the year 2000, another group measured it at 54.7, and after adjusting for limb darkening, they got a final size of 55.2. These numbers suggest a radius of about 5.6 AU, or more than 1,200 times the size of our Sun, assuming the star is about 197 parsecs away. In the year 2004, near-infrared measurements gave a smaller size of 43.33 milliseconds, which helped explain why different kinds of light give different results. By the year 2009, data from interferometers like IOTA and VLTI showed that Betelgeuse is surrounded by dusty shells and molecules, confirming that its outer layers are more complex than expected. Later studies in the year 2011 found similar sizes, with a diameter of 42.49 milliseconds. That same year, another measurement in the near-infrared showed a diameter of 43.33, and using a distance of 152 parsecs, astronomers calculated a physical size of about 3.4 AU, roughly 730 times the size of our Sun. Back in the year 2009, astronomers announced something rather surprising about Betelgeuse, one of the sky's most famous stars. Over a period of 16 years, from the year 1993 to the year 2009, the star had appeared to shrink in size by about 15%. To put that into numbers, in the year 1993, its angular diameter, how big it looks in the sky, was measured at 56 milliseconds, or mass for short. But by 2008, that size had dropped to just 47 mas. This decrease meant that the star's apparent size had shrunk by about 0.9 astronomical units, which is almost the distance from the Sun to the Earth. However, this shrinking probably didn't mean the star itself was actually getting smaller at its core. Instead, it was likely just the outer layers of gas and dust, what scientists call the extended atmosphere, that were shifting or cooling down. In fact, when astronomers looked at Betelgeuse in other types of light, such as infrared, they found that the star's size in those wavelengths had actually grown, suggesting that different parts of the star's outer layers were behaving differently. Today, most models estimate that the true surface of Betelgeuse, called the photosphere, is around 43 mass across. But the extended atmosphere of gas that surrounds it can stretch even farther, reaching out to around 50 or 60 mam. If we assume Betelgeuse is about 197 parsecs away, that's roughly 642 light years, then the star's diameter would be about 887 times wider than the radius of our Sun, with a margin of error of plus or minus 203 solar radii. That makes Betelgeuse truly colossal. For a long time, Betelgeuse held the record for the star, with the largest apparent size in our sky after the Sun. But that changed in the year 1997, when astronomers measured another red giant star named R Doradus. They found its apparent diameter to be 57 mass, slightly larger than Betelgeuse. But here's the catch: R Doradus is much closer to Earth, only around 200 light years away. So while it looks bigger, its true physical size is actually only about 1/3 the size of Betelgeuse. Betelgeuse shines in the mighty constellation of Orion the Hunter, far away from the path that planets follow across the sky, what astronomers call the ecliptic. Because of this, the big planets like Jupiter and Saturn never pass directly in front of Betelgeuse. These rare blink-and-you-miss-it events are called occultations, but every once in a while a tiny asteroid might cross in front of the star, briefly blocking a bit of its light from Earth. One such rare event happened on the 2nd day of January in the year 2012. A faint asteroid named 2005 UW381, which shines at 19th magnitude, so dim it's invisible without a powerful telescope, passed in front of Betelgeuse. But because Betelgeuse is much bigger in the sky than the asteroid, it only partially blocked the star. The result? A teeny dip in brightness, just 0.01 magnitudes, barely noticeable even with precise instruments. Another fascinating occultation was predicted for the 12th day of December in the year 2023. This time the asteroid involved was called 319 Leona, which shines at 14th magnitude, still too dim for the naked eye. Astronomers calculated that it might pass in front of Betelgeuse at 1:12 a.m, Coordinated Universal Time. At first, it wasn't clear if this occultation would be full or partial. If the asteroid covered the whole star, the event would last about 12 seconds, and only people within a narrow band on Earth would be able to see it. As more data came in, scientists updated their models and got a clearer picture. The final prediction showed that the occultation would produce a beautiful ring of fire effect, lasting for about 5 seconds. The narrow shadow, just 60 kilometers wide, would trace an impressive path across the globe, starting in Tajikistan, sweeping through Armenia, Turkey, Greece, Italy and Spain, crossing the Atlantic Ocean, then over Miami and the Florida Keys in the United States and finally ending in Mexico. Around 80 amateur astronomers from across Europe joined forces under the leadership of Miguel Montages at the Paris Observatory to observe and study this rare cosmic moment. Now let's take a closer look at Betelgeuse itself. This glowing red giant is a type of star known as an M-type supergiant, more specifically M1 to M2 Ia ab. The M means it's a relatively cool star with a deep red colour, and Yab means it's a bright supergiant, not the very brightest but still extremely luminous. In fact, Betelgeuse's light is so consistent that since the year 1943, astronomers have used it as a standard reference to classify other stars. But figuring out exactly how bright Betelgeuse is, that is, its luminosity, is tricky. We still don't know its exact temperature, size, or distance. However, in the year 2012, astronomers estimated that Betelgeuse shines about 126,000 times brighter than our Sun, assuming it's around 200 parsecs, or about 650 light-years, away. Since the year 2001, measurements of its surface temperature have ranged from 3,250 to 3,690 Kelvin. This temperature rises and falls because the star naturally pulses as if it's slowly breathing. Betelgeuse is a very slow spinner. Its latest recorded rotation speed is only 5.45 kilometers per second, much slower than that of another red supergiant Antares, which spins at about 20 kilometers per second. Scientists believe that Betelgeuse takes about 36 Earth years to make one full spin. But since the star is tilted at an angle of about 60 degrees from our point of view, we don't see this rotation directly. Even though it rotates slowly, Betelgeuse might still have magnetic activity in its massive outer layers. In the year 2004, astronomers using computer simulations suggested that strong magnetic fields might form in the star's atmosphere and help control how it loses mass. Then, in the year 2010, scientists used a special tool called a spectropolarimeter at the Bernard-Liot telescope in France and discovered a weak magnetic field on the surface of Betelgeuse. This hinted that the hot, churning gases inside the star, like boiling water in a pot, could be creating small magnetic dynamos even without fast spinning. Unlike some stars, Betelgeuse doesn't have a visible companion star orbiting it. This makes it hard for scientists to measure its mass directly. Instead, they rely on computer models. According to the latest estimates, Betelgeuse's mass is somewhere between 9.5 and 21 times the mass of the Sun. Older guesses were even wider, ranging from 5 to 30 solar masses. Based on its brightness, scientists believe Betelgeuse was born with a mass of 15 to 20 solar masses. In the year 2011, a new technique was introduced to figure out its mass more precisely. By analysing its infrared light in fine detail, scientists estimated Betelgeuse's current mass at around 11.6 solar masses, with possible values ranging from 7.7 to 16.6. A separate statistical analysis suggested its current mass is likely between 16.5 and 19 solar masses, and that it was born with 18 to 21 solar masses. Another approach is to study Betelgeuse's position on the colour magnitude diagram, which compares a star's colour to its brightness. A study in the year 2022 examined ancient records that hinted Betelgeuse might have changed colour over thousands of years, from yellow or orange to its current deep red. If this is true, it suggests Betelgeuse has a mass of about 14 solar masses, is about 14 million years old, and lies somewhere between 125 and 150 parsecs from Earth. That's about 400 to 500 light years. Betelgeuse's journey through space is also full of mystery. Stars that start life as massive as Betelgeuse, around 20 times the Sun's mass, usually live only about 10 million years. But if we trace Betelgeuse's path backward, it seems to have come from a place about 290 parsecs above the galactic plane, a spot where stars usually don't form. Also, its current path doesn't take it through the known star-forming regions of Orion, such as the 25 Orionis group or the much younger Orion Nebula cluster, also known as Orion OB1d. Measurements using the Very Long Baseline Array show that Betelgeuse is somewhere between 389 and 414 parsecs away from the Orion Nebula cluster. This has led scientists to believe that Betelgeuse might have changed direction in the past, possibly because of a powerful event, like a nearby supernova explosion. In the first month of the year 2013, astronomers using the Herschel Space Observatory made a remarkable discovery. They saw that powerful winds blowing off the surface of Betelgeuse, one of the biggest and brightest stars in the night sky, were smashing into clouds of gas and dust that fill the space between stars. This crash wasn't happening nearby, it was way out in deep space, showing just how far Betelgeuse's influence reaches. Even across many trillions of kilometers, the star still stirs the cosmic environment around it. Today, many scientists believe that Betelgeuse is a runaway star. This means it was once part of a family of stars, but for some reason, perhaps a powerful gravitational event, it was flung out of its original home and now races through space on its own. Astronomers think Betelgeuse was born about 10 to 12 million years ago, possibly as part of a massive group of stars called Orion OB1a. It likely formed as part of a multiple star system, where huge stars were packed close together. Because Betelgeuse is incredibly massive, it has burned through its fuel quickly and has already aged into the red supergiant we see today. However, not everyone agrees on its origin story. In the year 2015, researchers Hervé Bouy and João Alves suggested that Betelgeuse might actually belong to a different and newly discovered group of stars known as the Taurian OB Association. The mystery of where Betelgeuse truly came from is still being explored. As giant stars like Betelgeuse grow older, something dramatic happens. They begin to shed their outer layers, losing vast amounts of mass into space. In fact, a star like Betelgeuse could lose as much material as our entire Sun every 10,000 years. All this escaping gas and dust forms a thick, ever-shifting cloud around the star known as its circumstellar environment. Back in the year 2009, scientists released a study that underlined just how important this mass loss really is. They described it as a key process in understanding not only how stars change over time, but also how galaxies evolve and even how life might have begun. That's because the material released by dying stars enriches the universe with the elements needed for planets, and eventually living things. Yet, even now, scientists don't fully understand why or how this mass loss happens. Long before these recent discoveries, in the middle of the 20th century, a scientist named Martin Schwarzschild came up with an exciting idea. He suggested that the outer layers of stars like Betelgeuse are filled with giant bubbles of hot gas, called convection cells, that rise and fall like boiling water. These bubbling motions, he thought, might be pushing the outer layers of the star into space. Today, many researchers agree with him, but questions remain. How exactly are these bubbles shaped? How does dust form in such extreme conditions? And what finally causes stars like Betelgeuse to explode in a Type II supernova? In the year 2001, another scientist named Graham Harper estimated that Betelgeuse was losing material through stellar winds at a rate of about 0.03 solar masses every 10,000 years. But more recent studies, especially those carried out since the year 2009, show that the star might not be losing its mass in a steady stream. Instead, it may be shedding gas in bursts, like sudden fits of breath. This makes it much harder to figure out how much mass the star has lost in total. One surprising idea is that Betelgeuse might not stay a red supergiant forever. It may change stages again, briefly becoming a yellow supergiant, and then transforming into either a hot blue supergiant or a Wolf-Rayet star, a very hot and stripped-down version of a massive star nearing its final moments. Recently, astronomers made a stunning observation. They found a huge plume of gas stretching out from Betelgeuse, more than 6 times wider than the star itself. This discovery revealed that the star is not blowing out gas equally in all directions. Instead, it seems to release material unevenly, sending out more gas in some directions than others. When scientists look at stars in infrared light, the surfaces usually appear nice and round. But Betelgeuse looks very different. Using special instruments and a powerful telescope called the Very Large Telescope, astronomers saw lopsided patterns in the gas around the star. These could be caused by either giant convection bubbles under the surface or by gas being thrown out more strongly near the poles of the star due to its rotation. To understand even more, scientists used a tool called AMBER, which belongs to the European Southern Observatory. What they found was incredible. Enormous bubbles of gas were rising and falling violently, some almost as big as the star itself. This fierce activity likely created the giant plume seen by astronomer Pierre Cavella and his team. But Betelgeuse's atmosphere is not just a simple outer shell. In fact, scientists have discovered 6 extra layers beyond its main surface. Some of these layers are thick, some are thin, and some overlap like tangled clouds. One of these layers, just above the star's surface, is known as the mole sphere. It starts about 0.45 times the radius of the star, or roughly 2 to 3 astronomical units. That's the distance from the Sun to Earth multiplied by 2 or 3. The mole sphere holds molecules like water vapour and carbon monoxide, and it's heated to about 1,500 kelvins, give or take 500. Water vapour in Betelgeuse's light was first seen during the stratoscope missions in the 1960s, but was mostly ignored until more recent studies confirmed it, and even found other compounds like silicon monoxide and aluminum oxide, which help make dust grains. Farther out, there is a cooler gas envelope, stretching anywhere from 10 to 40 astronomical units from the star. This region contains more oxygen and nitrogen than carbon, probably because material from deep inside Betelgeuse, changed by nuclear fusion, has been brought up to the surface. In the year 1998, scientists used radio telescopes to take detailed pictures of Betelgeuse's atmosphere. They discovered that the gas had a temperature of about 3,450 kelvins, with some uncertainty of 850 kelvins. This is similar to the star's surface temperature but still cooler than expected. The same images showed that as gas drifts away from the star, it gets even cooler. Surprisingly, this cooler gas is the most common part of the atmosphere. One researcher, Jeremy Lim, explained how this discovery changed the way scientists think about red supergiants. Instead of a smooth, calm expansion of gas from the surface, it now looks like violent convection cells are throwing gas upwards, causing chaos. This is also where Cavella spotted the massive plume of gas, rich in carbon and nitrogen, extending 6 times the star's radius toward the southwest. The chromosphere, a hotter outer region of the star's atmosphere, was imaged directly by the Hubble Space Telescope using ultraviolet light. It showed a bright patch on the southwest part of the star's disk. In the year 1996, scientists found that the chromosphere extended about 2.2 times the visible size of the star, roughly 10 astronomical units, and had a temperature of up to 5,500 kelvins. In 2004, a more advanced tool on Hubble called STIS found warm plasma, or hot-charged gas, extending out to 1 arcsecond from the star. Since Betelgeuse is about 197 parsecs away, that means the chromosphere might stretch as far as 200 astronomical units. This hot plasma overlaps with cooler gas and dust, forming a swirling, complex outer atmosphere. The first idea that Betelgeuse had a dust shell came in 1977, when scientists noticed extra radiation coming from aging stars. Using a method called heterodyne interferometry, they figured out that most of this radiation came from beyond 12 times the star's radius, or about 50 to 60 astronomical units, roughly the distance of the Kuiper belt in our solar system. During the 1990s, more studies were done using different types of light, but the results didn't always agree. Some said the dust shell began at around 100 to 200 astronomical units, depending on how big they thought Betelgeuse was. It became clear that this dust wasn't steady. In 1994, scientists said the star was making dust in bursts that lasted decades, followed by quiet periods. By 1997, they noticed that the dust shell had changed shape drastically in just 1 year. This showed that bright spots on the star's surface were unevenly heating the dust. A strange study from 1984 claimed there was a huge lopsided dust shell 1 parsec away. That's over 200,000 astronomical units, but this hasn't been confirmed. Another study that same year suggested there were 3 dust shells stretching out as far as 4 light-years in one direction, which would mean Betelgeuse has been leaking material for an incredibly long time as it moves through space. The outer carbon monoxide shells are even harder to pin down. One may stretch from 1.5 to 4 arcseconds, and another might reach 7 arcseconds. If Betelgeuse has a radius of about 5.5 astronomical units, similar to Jupiter's orbit, then the inner shell would reach 300 to 800 astronomical units, and the outer one might go as far as 1,400 astronomical units. To compare, the heliopause, the outer edge of our Sun's influence, is about 100 astronomical units. So Betelgeuse's outer shell would be about 14 times the size of our entire solar system. Betelgeuse, one of the most famous stars we can see, is now a swollen, glowing red supergiant nearing the end of its life. But long ago it looked very different. It started as a blue-white O-type star, blazing hot and young. After it ran out of hydrogen fuel at its core, it changed into a blue supergiant and eventually expanded and cooled into the reddish-orange giant we see today. What's next for Betelgeuse will be truly spectacular. One day, its core will collapse under its own weight, setting off a powerful explosion called a supernova. What's left behind might be a neutron star, or if it's massive enough, a black hole. But exactly what happens next depends on how Betelgeuse was born, its mass, its spin, and its chemical makeup. Since no one was around to witness the birth of Betelgeuse, scientists have to rely on computer simulations and models to figure out what this giant star was like in its early life. These models use what we currently know about Betelgeuse, its size, brightness, chemical makeup, and how it behaves now, to work backward and guess its past. Even though there's still some uncertainty, most researchers believe that Betelgeuse started out with a mass somewhere between 10 and 25 times greater than the mass of our Sun. Newer and more precise models narrow that estimate down to between 15 and 20 times the mass of the Sun. When it was first born, Betelgeuse was mostly made of hydrogen, about 70%. The next biggest part was helium, making up roughly 28%. The last small fraction, around 2.4%, was made of heavier elements like carbon, oxygen and iron. This mixture isn't too different from what our Sun is made of, although Betelgeuse had just a bit more of those heavy elements, which astronomers often call metals. As for how fast Betelgeuse was spinning when it was young, that's harder to figure out. But scientists think it was spinning at a slow or moderate speed. That kind of rotation fits best with what we see in the star today. In its early years, Betelgeuse was what astronomers call an O-type main sequence star. These are some of the hottest, brightest stars in the universe. Betelgeuse may have been an O9 V-type star, a brilliant blue-white beacon in the sky, shining fiercely in its corner of the galaxy. Back then, it would have looked absolutely dazzling. Now, how long did it take Betelgeuse to grow into the massive red supergiant we see today? That depends mostly on how heavy it was and how fast it was spinning. A star with 15 times the mass of the Sun would take somewhere between 11.5 million and 15 million years to become a red supergiant. But more massive stars burn through their fuel more quickly. For example, a 20 solar mass star that spins slowly could reach this phase in just 8.1 million years. If the same star were spinning faster, it might take around 9.3 million years. Using these estimates, astronomers believe that Betelgeuse is now between 8 million and 8.5 million years old. But the question of how long Betelgeuse has already been a red supergiant is more difficult to answer. To get clues, scientists look at the clouds of gas and dust the star has blown off into space, and they also study the amount of heavier elements found on its surface. Some models suggest that Betelgeuse may have only been in this phase for about 10,000 years. Others stretch that number to as many as 140,000 years. Betelgeuse seems to go through periods where it suddenly loses a lot of material, and is also speeding through space, making things even harder to measure precisely. Still, the most commonly accepted estimate is that Betelgeuse has been a red supergiant for around 40,000 years, and that it probably left the main sequence about 1 million years ago. During its time as a red supergiant, Betelgeuse has already lost a good deal of mass, though not a huge amount. Models suggest that it has shed less than 1 solar mass, leaving it with a current mass somewhere between 19.4 and 19.7 times the mass of the Sun. However, some other ways of measuring, like watching how the star pulsates or fades at the edges, a phenomenon called limb darkening, suggest it might be even less massive. Any star that begins its life with more than 10 times the mass of the Sun is almost certain to end in a dramatic and violent explosion. For stars up to about 15 solar masses, this usually means going supernova as a Type 2P, an explosion that happens after the star becomes a red supergiant, just like Betelgeuse is expected to do. Stars that are even more massive can sometimes lose their outer layers more quickly. These stars might transform into yellow or blue supergiants, or even become rare and exotic Wolf-Rayet stars before they finally explode. Each of these paths can lead to a different kind of supernova, such as a Type 2L, Type 2B, or a stripped core explosion like Type Ib or Type Ike. For example, computer models suggest that a spinning star with 20 times the mass of the Sun could explode as something like supernova 1987A, a strange blast from a blue supergiant. But if that same star weren't spinning, it would probably end its life the old-fashioned way, as a red supergiant exploding in a Type 2P supernova, just like we think Betelgeuse will. So how much time is left before Betelgeuse finally explodes? That answer depends on how much time it has already spent in the red supergiant phase, and how massive it really is today. A rotating star with 25 times the Sun's mass might stay in this phase for about 300,000 years. A non-rotating star with 15 solar masses might last up to 1 million years. If Betelgeuse is a non-rotating star with 20 solar masses, then it might only have less than 100,000 years left before it goes supernova. But if it's spinning, or if it's less massive, then it could survive for much longer. Astronomers think that Betelgeuse was born in a group of stars known as the Orion OB1 Association, a sort of stellar nursery where many large stars formed. This region has already seen its fair share of powerful explosions. In fact, 3 fast-moving stars, Mu Columbae, AE Aurigae, and 53 Arietis, were likely kicked out of this area by earlier supernova blasts. These explosions probably happened around 2.2 million, 2.7 million, and 4.9 million years ago. When Betelgeuse finally reaches the end of its life, scientists expect it to explode as a Type 2P supernova. This kind of explosion is incredibly powerful. It would release around 2 times 10 to the power of 46 joules in the form of neutrinos, tiny particles that pass through almost everything, and another 2 times 10 to the power of 44 joules as kinetic energy from the blast itself. Seen from Earth, this explosion would be truly stunning. At its brightest, Betelgeuse might shine with a magnitude between -8 and -12. That would make it bright enough to be seen even during the day, and it might even rival the full moon in the night sky, though probably not outshine it. After the explosion, the light from Betelgeuse would stay incredibly bright for about 2 to 3 months. This glow would be powered by the radioactive decay of cobalt created during the blast. As the outer layers of the star cool down and become more transparent, the light would begin to fade, but even then, it would still be an unforgettable sight. When it happens, the explosion of Betelgeuse will be one of the most spectacular celestial events humanity has ever witnessed in all of recorded history. On the night of May the 8th in the year 1966, something extraordinary happened in the skies over Western Ireland. It was a cool spring evening, and the clouds drifted lazily across the stars. Amateur astronomer John Birmingham was walking home just before midnight. As he often did, he slowed his steps now and then, glancing up at the familiar constellations twinkling above. But that night, something stopped him in his tracks. As his eyes wandered toward the northern crown, also known as Corona Borealis, he noticed something strange. A new, bright star had suddenly appeared where there had never been one before. Birmingham had just witnessed an incredibly rare event, the dramatic outburst of a star known as T Coronae Borealis, nicknamed the Blaze Star. What he saw was a recurring nova, a type of explosive event in space so rare that it usually happens only once in a person's lifetime. That sudden burst of light marked the beginning of a new chapter in astronomy. Scientists around the world studied the Blaze Star's explosion closely, and over the following decades it helped shape our understanding of how stars evolve and interact. Now, more than 150 years later, in the year 2024, something amazing is about to happen again. The Blaze Star is preparing for another explosion, and this time, you won't need a telescope, binoculars, or any special equipment. If you look up at the right moment, you'll be able to see it with your own eyes. But why does this star keep exploding? And why does it happen every 80 years or so? Well, the nickname Blaze Star might sound like it's one star flaring up on its own, but the truth is a little more interesting. This is actually a binary system, which means it's made up of 2 stars locked together in a gravitational dance circling each other in space. And this close relationship is exactly what causes the explosions. In fact, scientists believe that around half of all the stars we see in the night sky are not alone, but part of double or even multiple star systems. Both of the stars in the Blaze Star system started their lives as ordinary medium-sized stars, much like our own Sun. But they are now in the later stages of their life cycles, further along than the Sun, which is about 4.6 billion years old. Our Sun is considered middle-aged. In another 5 billion years, it will run out of hydrogen fuel, begin to fuse heavier elements, and swell into a massive red giant. It may grow so large that it swallows up Mercury, Venus, and maybe even Earth. Eventually our Sun will shed its outer layers and leave behind a tiny but incredibly dense core known as a white dwarf, a dead star that has no more fuel and will take trillions of years to cool down completely. The Blaze Star system contains both a red giant and a white dwarf, and it's the interaction between these 2 aging stars that causes the nova. As the red giant puffs up and grows hotter, its outer layers of hydrogen are pulled away by the powerful gravity of its small, dense white dwarf companion. This process is slow and steady, like a cosmic vacuum cleaner sucking up gas. But as the white dwarf gathers more and more material from the red giant, the pressure and heat on its surface start to build up. Eventually there's too much to handle. Boom! The built-up gas explodes in a powerful thermonuclear blast, sending light and energy bursting out into space. You can imagine the white dwarf like a party popper. The string is pulled tighter and tighter as more material piles up. Then suddenly, snap! It goes off, spraying everything outward in a cosmic fireworks show. The result? A classic nova, a massive explosion that makes the Blaze Star shine up to 1,500 times brighter than normal. This incredible flash of light reaches Earth from a distance of about 3,000 light-years away and can be seen clearly in our night sky. No telescope needed. Now, you might be wondering how this compares to the more famous supernova explosions. While the Blaze star's nova is impressive, it doesn't completely destroy the white dwarf. Instead, the white dwarf survives and eventually begins collecting material from the red giant all over again, starting the slow process toward the next explosion. Supernovas, on the other hand, are much more violent. They happen when a star that's at least 8 times more massive than the Sun reaches the end of its life. These explosions are so powerful that they can shine millions of times brighter than a nova, and they leave behind either a neutron star or a black hole. One of the closest stars expected to go supernova sometime in the far future is the red supergiant Betelgeuse, which is often one of the 10 brightest stars in our night sky, even though it lies 640 light-years away. But don't panic. Scientists believe Betelgeuse won't explode for at least tens of thousands of years. That might sound like a long time to us, but in cosmic terms it's just around the corner. Still, if Betelgeuse did go supernova in our lifetime, it would be a sight to remember. For a while, it would shine as bright as the full moon and could even be seen during the day. Imagine looking up and seeing a second sun glowing in the sky. Even though supernovae are rare, they have been seen by humans before. The oldest known record of a supernova comes from Chinese astronomers, who in the year 185 during the Han Dynasty described a mysterious guest star that lit up the sky for 8 months. In more recent history, the famous German astronomer Johannes Kepler recorded a brilliant supernova in the year 1604, which was bright enough to see during the day. As for 2024, get ready. The upcoming Blaze star nova is expected to be one of the brightest classic novas of this entire century. Classic novas like this one do occur every year or two, but most are so faint that only professional astronomers with powerful telescopes can detect them. The Blaze star is different. It's going to be bright enough for just about anyone to see with the naked eye. In astronomy, scientists use something called the apparent magnitude scale to measure how bright a star appears when we look at it from Earth. The rule is actually a little strange. The lower the number, the brighter the star. So for example, a star with a magnitude of 0 is brighter than one with a magnitude of 1, and one with a magnitude of 1 is brighter than one with a magnitude of 2, and so on. It's like a countdown in brightness. Usually for a person standing under a clear dark night sky with no city lights around, the faintest star they can see with just their eyes, without binoculars or a telescope, has to be about magnitude 6.5. Anything dimmer than that needs help to be seen. To give you some perspective, the 7 stars of the Big Dipper, which is part of the constellation Ursa Major, have magnitudes ranging from 4.8, the faintest among them, to 1.7, the brightest. But the brightest star in the entire night sky is Sirius, which shines with a magnitude of -1.44. Yes, the scale even goes into negative numbers when stars are incredibly bright. And if you think that's impressive, consider the Sun. Our own star shines with a magnitude of about -26.5 during the daytime, which is why it's so overwhelmingly bright and outshines everything else. Now let's talk about a very special and mysterious star, the Blaze star. Most of the time it sits quietly with a magnitude of around 10, which means it's way too faint to be seen without a telescope. But something incredible happens roughly every 80 years. It explodes in a dramatic event called a nova. When that happens, its brightness suddenly increases, jumping all the way to a magnitude of between 3 and 2. That makes it visible to the naked eye, as if it suddenly appeared out of nowhere. One moment the sky looks normal, and the next a new star has burst into view. The word nova actually comes from the Latin word for new, and you can imagine how shocking this must have been before telescopes existed. People would have looked up and seen what looked like a brand new star lighting up the heavens. A good example from recent times is Nova Centauri 2013, which caught astronomers by surprise. It became one of the brightest novae seen in over 100 years, reaching a peak brightness of magnitude 3.3. The last time the Blaze star exploded was in the year 1946, and back then it brightened to a magnitude of 3. But now, in the second half of the year 2024, astronomers think it's about to happen again, and this time it might get even brighter. Some scientists predict it could reach a peak magnitude of 2, which would make it nearly as bright as Polaris, the North Star, which has a magnitude of 1.97. But this cosmic show won't last forever. Once the blaze star erupts, its brilliant light may only last a few days to a week before it fades back into the darkness, becoming invisible again to the naked eye. There's no way to predict the exact day it will happen, but experts believe the explosion could occur any day now, so this is a perfect time to keep checking the news and the sky. If you want to try spotting the blaze star during this event, here's how to find it. Look for the two constellations called Hercules and Bootes. Bootes is shaped like a kite, and Hercules is more of a lopsided rectangle. Between them lies a smaller curved group of stars called the Northern Crown, or Corona Borealis. The blaze star is located just beneath the last star in this crown-shaped arc, on the side closer to Hercules. If you have a good telescope or can visit a nearby observatory, you might even be able to catch a glimpse of the blaze star before it explodes. That would be a rare treat, seeing a star that's just waiting to burst into view. Events like this remind us that stars are not as unchanging as they seem. Even stars that appear steady and eternal can surprise us with sudden and dramatic changes. A nova is like a cosmic firework, a powerful and beautiful explosion that lights up the sky and gives astronomers a rare chance to study how stars live, evolve, and sometimes erupt. This coming nova might turn out to be one of the most exciting astronomical events of our lifetime. So if you get a clear night, take a moment to look up. Who knows? You might be lucky enough to witness a star being born all over again in a sudden burst of brilliant light. What a reminder that the universe is still full of surprises. You've probably heard that scientists today believe the universe is about 13.8 billion years old. That number sounds almost too huge to imagine. How could anyone possibly figure that out? It might seem like a wild guess, but the truth is, the method behind it isn't all that mysterious. It's just that most people don't stop to wonder how we arrived at that number. But here's where things get really interesting. A nearby star called Methuselah was discovered to be so old that it might actually be older than the universe itself, which sounds impossible, right? If the universe is about 13.8 billion years old, how could a star be even older than that? Let's explore how we even came up with the 13.8 billion year figure in the first place. Today we know that the universe is expanding. That means everything, galaxies, stars, clouds of gas, is slowly moving away from everything else. The only exceptions are places where gravity is strong enough to hold things together, like in galaxies or clusters of galaxies. This expansion happens at a measurable speed, known as the Hubble constant. Right now, we estimate that the universe is expanding at a speed of about 880,000 kilometers per hour for every million light-years of distance. That's incredibly fast. From this expansion, we can draw a few conclusions. First, it means that everything used to be much closer together in the past. Over time, as space itself stretched, galaxies drifted apart. The matter in the universe became more spread out or diluted. But there's another effect of this expansion that's not so obvious: the stretching of light waves. This phenomenon is called redshift. Right after the Big Bang, the universe was filled with light that was extremely energetic and had very short, high-frequency wavelengths, much like X-rays or gamma rays. But as the universe expanded, these waves were stretched out. Over billions of years, they became longer and less energetic, eventually reaching us as faint microwaves. This faint glow is called the cosmic microwave background radiation, a kind of ancient light left over from the early universe. That's why the James Webb Space Telescope was built to see in infrared light. The light from galaxies that are billions of light-years away has been stretched so much by the expansion of the universe that we can't see it with regular optical telescopes anymore. It's now in the infrared part of the spectrum. A photon, which is a particle of light, carries energy. The higher its frequency, the more energy it has. That also means it's hotter. So in the early universe, things were dense and hot. Today, they're spread out and cooler. So how does all of this help us figure out the age of the universe? Well, scientists start by making a few assumptions. On the larger scales, the universe is evenly filled with matter. This might sound wrong because we see areas packed with galaxies called superclusters and huge empty spaces called voids. But if you zoom out far enough, really far, it all averages out and looks the same everywhere. That's what we mean by homogeneous. The laws of physics are the same everywhere in the universe. What happens here on Earth follows the same rules as what happens on the far side of the universe. The Big Bang didn't happen in one spot. It happened everywhere, all at once. The entire universe was born at the same moment, not from a single point in space, but from space itself beginning to expand. If these assumptions hold true, and general relativity says they do, then there's a deep link between how fast the universe is expanding and how old it is. We can use various objects in space, like stars, galaxies, and supernovae, to help us measure distance and brightness. A special type of supernova, called a Type Ia supernova, always shines with about the same brightness, so if one appears dimmer than expected, it must be farther away. By knowing how dim it looks, we can calculate how far it is, and therefore how far back in time we're looking. We can also look at tiny variations or fluctuations in the cosmic microwave background. This glow is a snapshot of the universe when it was just a few 100,000 years old. By comparing those early patterns to the way galaxy clusters are arranged today, we can trace how the universe changed and grew over time. From these clues, scientists discovered something amazing about what the universe is made of. 68% of it is something called dark energy, 27% is dark matter, and only about 5% is the kind of matter we can actually see. Stars, planets, people, everything. Here's the strange part. We don't really know what dark matter or dark energy are, but we can see what they do. Dark energy is thought to be pushing the universe apart faster and faster. Without it, the expansion would have slowed down by now. Instead, it's speeding up. Dark matter, on the other hand, adds extra gravity. Galaxies and galaxy clusters behave as if they have way more mass than we can see. That extra pull is likely due to dark matter. Though we can't see it directly, we can map out its effects and even estimate where it is. Knowing how all of this works, how light stretches, how fast things expand, what the universe is made of, lets scientists work backward in time, step by step, to figure out how long ago everything began. When they do that, using different methods and different instruments, they all come back with about the same answer. The universe is roughly 13.8 billion years old, with an accuracy of about 99%. Another way to estimate the universe's age is to look at the oldest stars. Some stars burn through their fuel quickly and explode in a few million years. Others burn slowly and can last for trillions of years, though we haven't seen any that old yet. The oldest stars we've found are about 13.2 billion years old. That makes sense. They formed shortly after the Big Bang and are still shining today. But then there's Methuselah. This star is very unusual. It's extremely low in metal content, which means it formed very early in the universe's history. It's also very rare, and lucky for us, it's only about 200 light-years away, making it easy to study. Based on what we know about how stars evolve, Methuselah appears to be about 14.5 billion years old, older than the universe. There's some uncertainty in the measurement, plus or minus about 800 million years, but still, it raises big questions. So how can a star be older than the universe? Well, it probably can't. Most scientists think either our models of stellar aging need tweaking, or Methuselah's age was slightly overestimated. But it does show that our 13.8 billion year estimate may not be the final word. With new instruments like the Wide Field Infrared Survey Telescope, WFIRST, and James Webb Space Telescope, we might be able to peer even further into the past. It wouldn't be surprising if the estimated age of the universe changes a bit in the future, maybe by as much as 1 billion years in either direction. Even though this has been a topic of research for many decades, it's still early days in terms of our understanding. Just a few hundred years ago, people thought the universe had no beginning at all. Now, we're debating whether it's 13.8 billion years old, or maybe 14.5. That's a pretty amazing leap. If the universe had a museum filled with its most gigantic, brilliant, and astonishing stars, one of the first stars you'd see would be a giant known as the Behemoth. This star isn't just big, it's absolutely massive. And what's more, it doesn't even live inside our own galaxy, the Milky Way. Instead, it's located far away in a neighbouring galaxy called the Large Magellanic Cloud, a kind of cosmic companion that orbits near us like a satellite galaxy. The Behemoth is so enormous, so bright, and so strange that it has made scientists question what stars are truly capable of. It was first noticed back in the 1970s by 3 astronomers, Westerlund, Olander, and Hayden, and the star's official name, WOH-G64, comes from the initials of their names. Even in the early years after its discovery, the behemoth stood out for its mind-blowing size. Experts believe that the behemoth's radius, the distance from its centre to its outer edge, is about 1,500 times larger than the radius of our Sun. To grasp how immense that is, imagine the Sun placed at the centre of our solar system being replaced by the behemoth. Its outer layers would stretch so far that they would completely swallow up Mercury, Venus, Earth, and Mars, and would reach almost all the way to Jupiter's orbit. That's not just big, it's on a completely different scale. If you wanted a fun way to think about this, picture the Sun as small as a tennis ball. In comparison, the behemoth would be the size of an entire football stadium. That's how much more massive it is. But size is only part of its story. This monstrous star also shines with an unbelievable brightness. It produces about 280,000 times more light than our Sun. Yet, strangely, we can't see all of that light clearly. That's because the behemoth is wrapped in a thick swirling cloud of gas and dust shaped somewhat like a donut. This dusty shell was formed by the star itself as it shed parts of its outer layers, and it blocks a large part of the star's glow from reaching us. But this dusty cloak is not just an obstacle, it's a clue. It tells astronomers that the behemoth is probably nearing the end of its life. The material the star is throwing off into space isn't just a small cloud. It stretches almost 1 full light year across, which is close to 6 trillion miles. This cloud is slowly being pushed outward by strong stellar winds and the unstable outer layers of the star. It's like the behemoth is slowly peeling away its own skin, preparing for a dramatic end, possibly a powerful explosion known as a supernova. That kind of shedding is common in stars that are burning through their fuel much faster than they can handle. The behemoth is blazing brightly and using up its energy at an intense rate, and that cannot last forever. Now here's another twist. Even though the behemoth is so bright, its surface is surprisingly cool. Its temperature is only around 3,000 to 3,400 Kelvin, cooler than most stars. This lower temperature gives it a reddish glow, which is why it is placed in a group of stars known as red supergiants. These are giant stars that puff up and grow massive as they approach the final stages of life. But even among red supergiants, the behemoth is unusual. It may have gone beyond a special physical limit known as the Hayashi limit. According to this rule, a star of a certain size and mass should not be able to stay stable if it becomes too cool. But the behemoth seems to be ignoring that rule, and that has left scientists puzzled and curious. So here's a question. Is the behemoth really just one single star? Or could it actually be 2 stars, orbiting so closely that from far away they appear as one? Because of the thick dust around it and its far-off location, scientists can't say for sure. Some astronomers think there could be a second star hiding, maybe a hot bright blue O-type or B-type star just out of sight. If this is true, then the behemoth might actually be a binary star system, where 2 stars are locked in a close gravitational dance. If that's the case, the second star could be tugging on the behemoth or stirring up its layers, helping it lose material faster. But so far, no one has been able to confirm the presence of this hidden companion. It remains one of the great mysteries surrounding the behemoth. Another amazing part of this story is where the behemoth lives, the Large Magellanic Cloud. This galaxy is famous for being home to some of the universe's strangest and most massive stars. One reason might be the unique chemical makeup of this galaxy. It has fewer heavy elements, what scientists call metals, compared to the Milky Way, and that may allow stars here to grow larger, evolve faster, and die more explosively than stars in our own galaxy. The behemoth could be the perfect example of this phenomenon. It's a giant star shaped by the unusual environment it was born into. It breaks the rules and challenges what scientists thought they knew. And even today, it continues to baffle and inspire astronomers. Now, when we say the behemoth outshines the Sun, we're not talking about a small difference. The behemoth doesn't just shine a little more, it blasts out light with a force 280,000 times stronger than the Sun's. That makes it one of the brightest stars ever recorded anywhere in the universe. But what does that really mean in terms we can relate to? The total amount of energy a star gives off every second is called its luminosity. Our Sun's luminosity is about 3.8 times 10 to the power of 26 watts. That's more than enough to warm the Earth, drive the weather, and support life, all from a distance of about 150 million kilometers away. Now take that amount of energy and multiply it by 280,000. You get a truly gigantic number, about 1.064 times 10 to the power of 32 watts. That's an amount of energy so large it's hard to truly understand. It's not just like comparing a candle to a campfire. It's more like comparing a spark to the fiery destruction of an entire planet. The behemoth is a roaring, unstoppable furnace in the sky, so bright and so intense that it literally shapes its surroundings. This incredible brightness has real effects. The energy blasting out from the behemoth is so strong that it pushes against the star's own outer layers. This creates fierce winds of gas and particles that stream out into space. These stellar winds form enormous clouds of gas and dust, stretching out like waves from a powerful explosion in slow motion. Even though the behemoth is blasting out so much light, most of it isn't visible to the human eye. It shines mostly in the infrared and some visible wavelengths. If there were no dust in the way, the star would be so bright that we could spot it from other galaxies, millions of light years away. That's where infrared telescopes come in. Normal telescopes that use visible light can't see through the dusty clouds surrounding the behemoth. But powerful tools like the Very Large Telescope in Chile can detect infrared light. These instruments let astronomers study the star's spectral fingerprints, unique clues that tell them how much energy the star emits, what elements are swirling in its outer layers, and how quickly it is losing material into space. But all this breathtaking brightness and size come at a cost. The behemoth is not a young star. It's nearing the end of its life. Stars that burn so hot and bright use up their fuel quickly. They don't last long. The behemoth is burning through its life in a cosmic sprint, living fast, shining furiously, and preparing for a grand and fiery end. Even though our own sun still has around 5 billion years left before it runs out of fuel and reaches the end of its life, the colossal behemoth star has a much shorter future ahead. At best, it might live for only a few million years, which is incredibly short when you remember that the universe itself is over 13 billion years old. In the grand timeline of the cosmos, the behemoth's life is nothing more than the blink of an eye. The enormous amount of energy this star releases is a sign that it is burning through its life at full speed. It's almost as if we're watching a giant nuclear engine that's pushing itself to the edge, knowing that its time is quickly running out. And then there's its brightness. At first glance, it might seem breathtaking, even beautiful, but that glow hides a terrifying truth. The radiation pouring out of this star is far from harmless. It's powerful enough to break apart molecules, shred the delicate strands of DNA, and even strip away entire planetary atmospheres. If a planet was unlucky enough to orbit too close to this blazing giant, it would be a death sentence. Any life on that world would be burned away in seconds. The light and heat would not warm it, they would destroy it. So if you were looking for a friendly star to live beside, the behemoth would be the worst possible choice. There is nothing warm or welcoming about it. This star is not gentle or calm, it's wild, violent and unpredictable. It floods everything around it with burning heat, blinding light, and unstoppable destruction. It's more like a cosmic storm than a star. What's even more unsettling is that this star doesn't shine with a steady glow. It pulses, it flickers, it grows brighter, then dims, then brightens again, like it's breathing or trembling from deep within. Scientists believe these strange changes are caused by something happening inside the star's core. Maybe wild storms of energy, or waves of pressure building up and crashing down. Each flicker might be a clue. Maybe the star is beginning to collapse in on itself, maybe it's preparing for a massive explosion, or maybe something far stranger is going on beneath its surface. But here's the question. Why would scientists want to study something so dangerous, so short-lived, and so unpredictable? Because the behemoth star is one of the rarest and most extreme kinds of stars in the universe, and by watching it, scientists can learn how the biggest stars are born, how they live, and how they die. These massive stars help shape the galaxies we live in. They create the heavy elements, like gold, iron, and uranium, that make up planets, and even our own bodies. Studying a star like the behemoth is like getting a front row seat to one of the universe's greatest and most dramatic performances. Watching it is like seeing a slow-motion replay of a cosmic disaster, one that teaches us how stars change over time, how galaxies grow and evolve, and how the universe has become what it is today. When the behemoth star reaches its final moments and goes out in a blaze of fury, it will leave behind more than just ashes. It will leave behind answers. It will tell a story that began billions of years ago, a story of fire, light, death, and rebirth. And by studying that story, we come closer to understanding the secrets of the stars themselves. A subgiant star is a special kind of star that lives in the space between two well-known types of stars. It shines more brightly than an average star like our Sun, which is called a main sequence star, but it isn't as huge or as brilliant as the massive giant stars. The word subgiant has two meanings. It refers to both a specific group used in star classification based on brightness, and a particular phase in a star's long life as it ages and changes. The term subgiant was first used in the year 1930. Back then, astronomers noticed that some stars, particularly those in the G and early K spectral types, had brightness levels between plus 2.5 and plus 4 in absolute magnitude. These stars didn't quite fit with either the main sequence stars like our Sun, or the larger, more luminous giants like Aldebaran. So, subgiants were introduced as a sort of missing link, bridging the gap between the two. While not as common as stars in the other categories, subgiants turned out to be a very important piece of the puzzle when it came to understanding how stars evolve. Astronomers use a system called the Yerkes spectral classification to organize stars. This system uses letters and numbers, like a 5 or M1, to describe how hot a star is, and it also uses Roman numerals to show how bright a star is when compared to others of the same temperature. In this system, main sequence stars are labelled with Roman numeral 5, giants are labelled with Roman numeral 3, and subgiants fall in between with Roman numeral 4. To figure out which category a star belongs to, astronomers don't just look at how bright it appears. Instead, they carefully study its light spectrum, the pattern of light the star gives off, and compare it to stars they already understand. Certain details in the spectrum, like the width and depth of specific absorption lines, can tell scientists how strong gravity is at the star's surface. That clue helps them decide whether the star is a main sequence dwarf, a subgiant, or a giant. Later on, as scientists improved their instruments and techniques, they discovered that some stars labelled as subgiants were actually two stars close together, whose combined light made them appear brighter. Others turned out to be variable stars, stars that change in brightness over time. Even so, many of the original subgiants from those early days are still used as the standard examples for this group. Interestingly, stars at the extreme ends of the temperature scale are rarely classified as subgiants. Very hot stars known as O-type and very cool stars cooler than K1 almost never fall into the subgiant category. The term subgiant branch is also used to describe a stage in the life of low to medium mass stars like our Sun. But just because a star is called a subgiant doesn't always mean it is going through the subgiant phase, and vice versa. For example, stars like FK Comae Berenices and 31 Comae Berenices are believed to be in the subgiant evolutionary phase, even though they are sometimes labelled as giants. This confusion happens because a star's classification depends on more than just brightness. Things like how fast the star spins, how much metal it contains, and even unusual chemical elements can affect how it's labelled. As a star like our Sun grows older, the hydrogen fuel in its core slowly runs out. When this happens, the core begins to shrink and heat up, which causes the surrounding hydrogen to burn faster. The star becomes brighter, and it starts to leave the main sequence, beginning its journey toward becoming a subgiant. On a special kind of star chart called the Hertzsprung-Russell diagram, this shift is seen as a widening of the band that represents main sequence stars, because stars get brighter as they age. When all the hydrogen in the core is gone, the core collapses further and gets even hotter. Now, instead of hydrogen burning in the centre, it burns in a shell surrounding the core. This shell burning releases more energy than before, causing the star's outer layers to expand and cool down. When the surface temperature drops to around 5,000 kelvins, the star becomes even brighter and begins to climb the red giant branch. The short period in between, when the star is no longer a main sequence star but not yet a giant, is the subgiant phase. The way this subgiant phase plays out depends a lot on the mass of the star. For example, stars with less than 40% of the Sun's mass, also written as 0.4 solar masses, are mostly made of convective material. This means that heat and particles move around the star like boiling water in a pot. These stars keep burning hydrogen throughout their entire interiors and never enter a true subgiant phase. In fact, their lives on the main sequence last so long, many times longer than the age of the universe itself, that we have never seen one move beyond it. On the other hand, stars with at least 40% the mass of the Sun develop a more layered structure, with a central core that is no longer convective. As soon as the core runs out of hydrogen, hydrogen burning shifts to the surrounding shell. At this point, even though the star is technically a subgiant, the surface doesn't change much, at least not yet. As the hydrogen shell keeps burning, it creates helium, which builds up in the core. The energy from this process causes the outer layers of the star to swell outward. Depending on its mass, the star can grow to be between 2 and 10 times its original size. However, the surface temperature doesn't change much, so its spectral class stays mostly the same, especially for stars on the lighter side of this range. But the bigger the star's surface area, the more energy it radiates. For example, if a star has a radius that is twice as large as the Sun's, it shines with 4 times as much power. If its radius is 10 times larger, it radiates 100 times more energy. This enormous increase pushes the habitable zone, the region where a planet could have liquid water, farther away from the star. During this phase, the helium core is still not hot enough to start helium fusion. Instead, it remains balanced under the pressure of the hydrogen-burning shell around it. As the shell burns more hydrogen, the core gathers more helium, and the star's outer layers keep expanding. Interestingly, the star's brightness stays nearly the same. That's why, in star clusters, this stage appears as a short horizontal line on the star chart known as the subgiant branch. Eventually, after anywhere from 1 billion to 8 billion years, the helium core becomes so massive that it can't support its own weight anymore. At this point, it becomes degenerate, meaning it is held up not by normal gas pressure, but by quantum mechanical forces. This causes a chain reaction. The temperature rises quickly, the shell burns faster, the outer layers become unstable and start churning, and the star gets much brighter, even though its surface temperature stays mostly the same. This is when the star fully enters the red giant phase. Stars with masses similar to the Sun, or even larger, act quite differently from smaller stars. While they are still on the main sequence, they have a central zone where materials are constantly mixing due to convection. Over time, this mixing builds a large helium core deep inside. Even before the star completely runs out of hydrogen in that central zone, the core is already taking up a big portion of the star's interior. Eventually, fusion stops in the center because there is no more hydrogen left. With no energy pushing outward, the core shrinks and heats up. This also makes the whole star contract, and its temperature rises. Oddly enough, even though fusion has stopped, the star actually gets brighter during this time. This heating and shrinking can continue for several million years. Then, the temperature around the core gets high enough to restart hydrogen fusion, but only in the shell around the core, not the core itself. When this shell fusion starts, the star's surface temperature and brightness stop rising. Instead, the outer layers begin to swell, and the star starts to cool down. This moment of transition from heating up to expanding is seen as a small kink in its path on the Hertzsprung-Russell diagram. Astronomers use that kink to mark the end of the main sequence and the beginning of the subgiant phase. When stars reach a certain point in their lives, they start to change in quiet but powerful ways. For stars that are less than about 2 times the mass of our Sun, their inner helium core is still smaller than a special limit known as the Schoenberg-Chandrasekhar limit. This limit is like a balancing point. As long as the helium core stays smaller than this, it can remain stable. But once the hydrogen fuel in the outer shell starts burning more rapidly, the core quickly becomes heavier. Soon, it crosses that limit, and everything changes. Stars that are more massive than this don't wait around. Even before they leave the long and stable main sequence phase, where they spend most of their lives, their cores are already heavier than the Schoenberg-Chandrasekhar limit. These stars are built for speed, and their changes come sooner. Now, what exactly decides when a star hits this turning point? There are two big factors. First is metallicity. This is how many heavy elements the star has. In astronomy, anything heavier than helium is called a metal, even elements like carbon and oxygen. The second factor is called core overshooting. This refers to how far the turbulent mixing inside the star's core reaches beyond its normal boundary. Stars with fewer heavy elements, or low metallicity, can have cores that are unstable and prone to convection, even if they're not very big. And when overshooting happens, it can cause the core to grow larger than usual before the hydrogen gets completely used up. Once the helium core becomes too massive to stay balanced with the surrounding hydrogen-burning shell, it begins to collapse. The outer layers of the star respond by expanding and cooling down. This dramatic swelling takes energy away from the star's center, causing the star's overall brightness to drop. But then something interesting happens. As the outer layers cool, they become opaque, like foggy glass, and this triggers a new kind of convection just above the fusion shell. The star stops expanding, and its brightness starts to rise again. This moment marks the beginning of the red giant phase. For stars that started off with about 1 to 2 times the mass of the Sun, the core might already have turned into a dense ball of helium, what scientists call a degenerate core, before this transformation even begins. This behavior is very similar to what we see in smaller stars. The whole stage, from the collapse of the core to the swelling of the outer layers, happens quickly in terms of cosmic time. It usually takes only a few million years. During this time, the star's surface temperature drops significantly. While on the main sequence, stars typically have surface temperatures between 6,000 and 30,000 degrees Kelvin, but during this transition, their temperatures can fall to around 5,000 degrees. Because this phase is so short, astronomers don't see many stars in this stage. As a result, there's a noticeable gap on star charts, particularly on the Hertzsprung-Russell diagram, also known as the HR diagram. This gap is called the Hertzsprung gap, and it stands out clearly in star clusters that are between a few 100 million and a few billion years old. Now, if a star starts out with 8 to 12 times the mass of the Sun, or even more, things happen even faster. These heavyweights have large hot cores where energy is generated through the powerful CNO cycle, a fusion process that dominates in massive stars. Once the core's hydrogen is gone, both hydrogen shell burning and helium core fusion begin almost immediately. These stars don't even have time to puff up and become red giants. Instead, they skip ahead, passing through a brief subgiant stage and head straight into becoming supergiants. Some are briefly called giants based on the light they emit, but that stage is incredibly short. In the case of the most massive stars of all, the mighty O-class main sequence stars, the transformation from main sequence to supergiant is squeezed into a very narrow band of temperatures and brightness. Some of them might even start becoming supergiants before they finish burning all their hydrogen. Because this in-between phase is so brief and complex, astronomers often don't bother labeling them as subgiants. To classify stars during these transitions, astronomers use a measure of surface gravity known as log-G. For example, an O-type dwarf star, a smaller, hotter star, has a log-G of about 3.9. An O-type giant has a slightly lower value of around 3.6. A cooler K-type giant like Aldebaran has much lower surface gravity, about 1.59. A smaller star like Alpha Centauri b has a much higher log-G, near 4.37. A subgiant such as Eta Cephei sits neatly between these extremes, with a log-G of around 3.47. Other famous massive subgiants include Theta 2 Orionis A and the primary star of Delta Cassini. Both are O-type stars with more than 20 times the mass of the Sun. Stars with fewer heavy elements behave differently. They tend to be hotter and more compact than stars with lots of metals. For subgiants, this makes their evolution more complicated. A star's age and the size of its helium core when it leaves the main sequence can vary depending on its metallicity. Stars with low metallicity often grow larger helium cores before they exit the main sequence. This means that even stars with modest mass can enter the subgiant phase and show a distinct hook shape in the HR diagram. For example, a star with the same mass as the Sun but with very low metallicity, let's say 0.001, is classified as an extreme population 2 star. By the time it leaves the main sequence, its helium core can be almost twice as massive as the core of a high metallicity population 1 star, metallicity around 0.02. That low metallicity star will also be over 1,000 degrees hotter and more than twice as bright when it begins its subgiant life. As time goes on, the temperature difference between the two stars gets smaller, but the low metallicity star still ends up larger and almost 4 times brighter at the end of the subgiant stage. This pattern holds true for stars of many sizes. In fact, the minimum mass required for a star to become a supergiant, instead of just a red giant, is lower in low metallicity environments. The HR diagram is like a cosmic family photo. It helps astronomers track a star's entire life by comparing its brightness and temperature. On the horizontal axis, left to right, we see either the star's temperature or spectral class. On the vertical axis, up and down, we see how bright or luminous the star is. Most stars fall along a big slanted band called the main sequence. This is where stars spend most of their lives, burning hydrogen quietly and steadily. But the diagram also shows the red giants, older stars that have expanded and cooled, and white dwarfs, the hot dim leftovers of stars like the Sun. Some parts of the diagram are nearly empty because not every star goes through every phase. Subgiants show up in a small region just above the main sequence. They are brighter than main sequence stars, but not as big or bright as red giants. However, because the subgiant phase is so short, we don't see many of them at any given time. The hot subgiants, especially those from spectral class B, often look a lot like main sequence stars and are hard to identify. But the cooler subgiants stand out more clearly. They fill the wide gap between the cool end of the main sequence and the red giant branch. Interestingly, below spectral type K3, that space is completely empty. No subgiants exist there. Astronomers can also trace the life paths of stars on the HR diagram using evolutionary tracks. These are like time-lapse trails showing how a star changes over time. In star clusters, where many stars were born at the same time, the subgiant path appears as a clear band between the main sequence turn-off point and the red giant branch. But this subgiant band is only visible in old star clusters, those that are at least a few billion years old. That's how long it takes for stars with between 1 and 8 times the mass of the Sun to reach the subgiant phase. Famous clusters like Omega Centauri and Messier 67 are old enough to show this beautifully. Omega Centauri is especially puzzling. It doesn't just show one subgiant branch, it shows multiple. The best guess so far? Omega Centauri might be hiding a secret history. It could contain several generations of stars, each born at different times, all living together in the same cosmic neighborhood. Some subgiant stars that are more massive than the Sun go through an area of the HR diagram known as the Cepheid instability strip. This happens during their first crossing of the strip, although some stars may pass through this strip more than once during a later stage known as a blue loop. Stars with weights between about 2 and 3 times the weight of the Sun may become delta Scuti variables, which are stars that change in brightness. One example of this kind of star is Beta Cassiopeiae. If the stars are even more massive, they may become classical Cepheid variables during their crossing of the instability strip. However, because these massive subgiant stars change very quickly, it is quite rare and difficult to catch them in this short stage. One star, SV Vulpeculae, was once thought to be a subgiant on its first crossing of the strip, but later studies showed it was actually on its second crossing. Skywatchers have also found planets going around subgiant stars. Some examples of these star-planet systems include Kappa Andromedae b, Kepler 36b and c, TOI 4603b, and HD 2 24693b. A hypergiant star is one of the rarest and most extreme kinds of stars in the entire universe. These stars are not just large, they are truly colossal. They shine with a brightness that can seem almost unreal, are many times the size of our Sun, and constantly throw off huge amounts of gas from their outer layers. This happens because the light and energy coming from inside them are so intense that they blow their own surface apart, creating powerful streams of gas called stellar winds. Astronomers use a special system to group and classify stars called the MKK system. In this system, hypergiants fall under a category called luminosity class 0. But you won't often see this class 0 label written in scientific research. Instead, scientists usually use it only for very unusual stars, such as yellow hypergiants, red supergiants, and blue supergiants, especially those that give off strong glowing features in their light, known as emission spectra. More often, hypergiants are labelled with terms like Ia 0 or Ia+, while red supergiants, even when they are massive, usually don't get this special classification. So, why are astronomers so fascinated by hypergiants? Because these enormous stars offer us clues about the life cycle of stars, how they are born, how they evolve, and how they meet their spectacular ends, often in massive explosions known as supernovae. Some of the most famous hypergiants include the Pistol Star, a blue hypergiant located near the centre of our galaxy. It is one of the brightest stars ever found. Rho Cassiopeiae, a yellow hypergiant that is so bright it can actually be seen with the naked eye from Earth. Mu Cephei, also called Herschel's Garnet Star, is one of the largest and most brilliant stars astronomers have ever observed. Back in the year 1956, two astronomers named Feast and Thackeray came up with the term supergiant to describe stars that were brighter than an absolute magnitude of -7, which is extremely bright. Later on, this term was changed to hypergiant. In the year 1971, another astronomer named Keenan suggested that the word hypergiant should only be used for those supergiants that show a wide glowing line in their light spectrum called the H-alpha emission line. This feature suggests the star has a huge extended atmosphere and is losing mass quickly. Today, most scientists still follow Keenan's rule, so strangely enough, a regular supergiant can sometimes shine more brightly than a hypergiant of the same type. It's not just about brightness, but about what's happening in the star's atmosphere. One of the main ways astronomers can tell if a star is a hypergiant is by looking at the details in its spectral lines, the patterns of light that reveal what the star is made of. In many hypergiants, these lines are stretched and shifted toward the red end of the spectrum. This pattern is called a P-Cygni profile. But when hypergiants are cooler, meaning their surface temperatures are lower, this method doesn't work very well. In those cases, astronomers rely more on how bright the star is and how fast it is losing mass. Stars that are born with more than 25 times the mass of the Sun don't stay in their youthful stage, called the main sequence, for very long. They quickly evolve into blue supergiants, which are hot and bright. Then they expand and cool down into red supergiants, often without changing brightness too much. After that, they might shrink and heat up again, switching back and forth between hot and cool stages in what scientists call blue loops. Eventually, they either explode in a supernova or shed their outer layers and become a special kind of extremely hot star called a Wolf-Rayet star. But if a star is born with more than 40 times the mass of the Sun, it's simply too powerful to ever become a red supergiant. These stars are so luminous that their outer layers are blown away by their own light before they ever get a chance to cool down. The most massive stars of all, especially those that spin quickly and mix their inner layers more, might skip all the intermediate steps and go straight to becoming Wolf-Rayet stars. Hypergiants sit at the very top of the Hertzsprung-Russell diagram, a chart astronomers use to compare stars by how bright and hot they are. Some hypergiants are young, massive stars that have just left the main sequence. Others are older stars that already passed through the red supergiant stage and lost a lot of their mass. But just by looking at their brightness and temperature, it's hard to tell which is which. Young hypergiants still have a lot of hydrogen in their cores, which helps them stay stable. But older ones have burned up most of their hydrogen and are filled with heavier elements. These stars become unstable. Their atmospheres swell up and get harder to hold together. The light and radiation coming from inside them creates so much outward pressure that it almost tears the star apart. These stars are said to be near the Eddington limit, the tipping point where radiation nearly defeats gravity. These are the stars we call hypergiants. Yellow hypergiants are thought to be stars that have already passed through the red supergiant phase and have lost most of their outer hydrogen-rich layers. Some yellow supergiants are still moving toward the red supergiant stage, but that step is very short and rare. Because yellow hypergiants are usually in the later stages of their lives, their brightness is limited to about 500,000 to 750,000 times the brightness of the Sun. Blue hypergiants, however, can shine as brightly as several million suns. Most hypergiants don't shine with a steady light. Their brightness changes slightly because of violent and unpredictable movements happening inside them. In certain regions, especially where luminous blue variables, LBVs, and yellow hypergiants exist, these brightness changes can be quite dramatic. Hypergiants don't live very long. While a star like our Sun can live for about 10 billion years, a hypergiant might survive for only a few million years. They are born in the largest and busiest star-forming regions in space. Because they burn their fuel so quickly and die young, astronomers have only found a small number of them, despite the fact that they shine so brightly that they can even be seen in galaxies outside our own. Some stages in their lives, like the LBV phase, may last only a few thousand years. That's an incredibly short time when compared to the billions of years that make up the history of the universe. Hypergiants are not just large, they're blindingly bright. The more massive a star is, the brighter it becomes, but this brightness has a limit. As a star gets brighter and more powerful, it can reach the Eddington limit, a dangerous balance point where the energy pushing outward from inside the star becomes nearly strong enough to overpower gravity, which tries to hold the star together. In simple terms, you can think of gravity as the star's hands trying to keep everything from flying apart, while the light it produces is like a powerful wind pushing everything outward. If the light becomes just a bit stronger than gravity, the outer layers of the star start to tear away and fly into space. Once the star goes past this Eddington limit, it begins to lose mass in violent bursts, throwing off enormous amounts of material. These explosive outbursts actually act like a safety switch, preventing the star from getting even brighter and more unstable. A dramatic example of this is Eta Carinae, one of the most extreme stars known. Scientists think Eta Carinae might have about 130 times the mass of the Sun, and its brightness is estimated to be around 4 million times greater than the Sun's. Astronomers believe that Eta Carinae went beyond the Eddington limit at least once, possibly between the years 1840 and 1860, during a time of massive eruptions. During this period, it lost mass at a rate far beyond what current science says should be possible through normal stellar winds. Stars often lose parts of themselves over time. This happens through powerful winds made of gas and particles, pushed outward by the energy of light escaping the star. In most stars, this process is driven by what scientists call line-driven radiation. In simple terms, certain atoms in the star's outer layers absorb specific colors or wavelengths of light. This energy gives the atoms a push, helping to fling material out into space. But when it comes to hypergiants, some of the most powerful and extreme stars in the entire universe, things get even more intense. A famous example is Eta Carinae, a monstrous star whose energy is so extreme that it may rely on something even stronger: continuum-driven winds. This type of radiation pressure is so powerful that it doesn't need the help of atoms like carbon or iron to drive material away. That's important because many of the oldest and most massive stars in the universe, especially those born shortly after the Big Bang, are what astronomers call metal poor. They barely have any elements heavier than helium. This idea of continuum radiation could explain how the very first stars ever formed, stars that had almost no heavy elements, were still able to blow away material and control their size. It might even be the reason why stars can only grow so big before something in nature stops them from becoming larger. Another fascinating theory is that hypergiants might occasionally experience enormous explosions deep inside themselves. These blasts wouldn't happen on the surface, but far below in the star's inner layers. The trouble starts when heat can't move around properly, a process called convection. If the heat gets trapped, the star's internal structure might become unstable. In this kind of situation, the denser material might suddenly rise instead of sink, triggering a violent burst that could launch huge chunks of the star into space. Scientists are still studying this idea. It's exciting but not yet fully understood. There's also a strange and mysterious phenomenon known as a pseudo-photosphere. Normally, the photosphere is the layer of a star we can see, the place where its light escapes into space. But in hypergiants, especially ones with very strong winds, this outer surface might actually be an illusion. What we see could just be a thick cloud of gas blown out by the star, forming a false outer layer. This wind-made shell would be much cooler than the actual star hiding beneath it. That might be why some super bright stars like yellow hypergiants appear cooler than they really are. These cooler-looking stars might in fact be luminous blue variables or LBVs wearing a mask of gas. Hypergiants are enormous, evolved stars that shine with staggering brightness. On the Hertzsprung-Russell diagram, a tool astronomers use to plot stars by their brightness and temperature, hypergiants often overlap with other types of stars. This makes them tricky to classify. Are they truly a different kind of star, or are we just catching them at different moments in their wildlife cycles? It's hard to say for sure. Even supergiants, which are already massive, usually aren't as bright or dramatic as hypergiants, although a few come close. What truly sets hypergiants apart is how unstable they are. They lose mass rapidly, and their light often shows strong signs of hydrogen gas being pushed out into space. Stars that start with slightly less mass often skip the red supergiant stage entirely, and either explode as supernovae or shrink into dense white dwarfs. One rare and fascinating type of massive star is the luminous blue variable, LBV. These stars are hot, incredibly bright and full of surprises. Most of the time they stay calm in a hot, bright corner of the diagram, but every now and then they erupt in dramatic outbursts, throwing off material and cooling down. During these events, they slide across the diagram to a zone where stars settle at around 8,000 degrees Kelvin, which is roughly 13,940 degrees Fahrenheit. This area is close to where we find yellow hypergiants, a region known for instability. Scientists still don't know if yellow hypergiants ever transform into LBVs, or if they take a different path and explode. Blue hypergiants live in the same zone as LBVs, but don't always behave the same way. Some LBVs sometimes look like hypergiants, and some blue hypergiants show LBV-like traits. But not all astronomers agree on how to label them. One idea is that blue hypergiants might become LBVs, or maybe the other way around. Others think some lighter mass LBVs could be evolving into yellow hypergiants, or that these stars are something else entirely. Then we have the Wolf-Rayet stars, among the hottest stars known. These are stars that have already blown off most of their outer layers. One subgroup, called WNL stars, which stands for late-type Wolf-Rayet stars, is slightly cooler and shows signs of nitrogen in its light. Some scientists believe that hypergiants might eventually lose enough mass to become WNL stars. But there's a twist. Some Wolf-Rayet stars that still have hydrogen may actually come before the hypergiant stage. They might be the ancestors of blue hypergiants or LBVs. There are also a few in-between types, like OFP and WN9 stars. These may represent very short-lived phases between regular massive stars and hypergiants. Interestingly, some LBVs in their calm phase look just like WNL stars, and a few OFP WNL stars have suddenly changed their appearance, becoming more like blue hypergiants. Scientists now believe that if a massive star spins fast enough, it can throw off its outer layers very quickly. This rapid spinning might allow the star to skip the supergiant phase altogether and jump straight to the Wolf-Rayet stage. Despite their intense light and fierce stellar winds, stars like Wolf-Rayet stars/stars, cool/stars, OFPA, OFP+, and OFF are not officially classified as hypergiants. They form their own unique families, each with distinct traits in their light signatures. Hypergiants are not only incredibly rare, they're incredibly complicated. They're like cosmic shapeshifters. Their light, which carries clues about what's happening inside, changes often. These shifts make it hard for astronomers to pin down exactly what these stars are doing at any given time. Because of this, scientists usually group hypergiants into broad categories, based more on general patterns than fine details. Some of the most exciting hypergiants are also LBVs, stars that go through dramatic mood swings over the course of their lives. In fact, many LBVs are only considered hypergiants during certain phases. Here are some of the most legendary examples. AG Carinae is a massive LBV star found in the southern sky, in the Carina constellation. It's currently undergoing a major transformation from a blazing hot O-type star into a stripped-down Wolf-Rayet star. Eta Carinae, possibly the most famous of all, also lives in the Carina constellation, inside the breathtaking Carina Nebula, known officially as NGC 3372. Eta Carinae is a true beast. It has somewhere between 120 and 150 times the mass of our Sun. Its brightness is staggering, 4 to 5 million times brighter than the Sun. Some scientists believe this star may be something even more unusual than a typical LBV. Piscini, in the northern constellation Cygnus, is one of the first LBVs ever discovered. It serves as the classic model for what an LBV's light spectrum looks like. S Doradus, found in the nearby Large Magellanic Cloud Galaxy in the southern constellation Dorado, is another iconic LBV. In fact, for many years, these stars were called S Doradus variables because of how well this star represents the group. The Pistil star, officially named V4647 Sagittarii, is located near the very heart of our Milky Way galaxy, in the constellation Sagittarius. It is more than 25 times the mass of the Sun and glows with the energy of about 1.7 million suns. Scientists suspect it might be an LBV, but they're still not sure whether it truly changes brightness over time. Not every hypergiant is blue. Some are yellow hypergiants, and a few can appear white. Yellow hypergiants usually fall between spectral types late A and early K, which means they're cooler than blue stars but still incredibly hot compared to most stars. If an A-type hypergiant shines especially bright, it might even be called a white hypergiant. These colour shifts, wild outbursts, and mysterious changes make hypergiants some of the most fascinating and puzzling stars in the universe. They challenge everything we know about how stars live, evolve, and die. There are also some hypergiant stars that are much cooler than the extremely hot and bright ones. These cooler giants appear red or orange when seen in the sky. A few of them have been found in recently discovered groups of massive stars known as the scutum-red supergiant clusters. Within one of these clusters, called RSGC-1, astronomers have identified a star named F15. It might be joined by another giant star called F13. In another nearby cluster, named RSGC-2, there is a star known as Star 49. These cool or red hypergiants usually belong to the K and M classes in the star classification system, which means they are not only cooler in temperature, but also among the largest stars ever recorded in terms of size. Some of them are absolutely colossal, with radii ranging from about 1,000 to 2,000 times wider than the Sun. To put that in perspective, if one of these enormous stars were placed where the Sun is in our solar system, its surface would stretch far past the orbit of Jupiter, possibly engulfing everything from Mercury to Mars and beyond. Even though scientists usually don't give these red supergiants the official hypergiant title, the term red hypergiant is sometimes used to describe the most extreme cases, those that are incredibly bloated and highly unstable, often shedding mass as they near the end of their lives. Red supergiants are among the biggest stars we've ever discovered, true giants that tower above most others in the universe. These enormous stars belong to a group astronomers called the supergiant class, officially named Luminosity Class 1 in the Yerkes or Morgan-Keenan system. When it comes to size, red supergiants are unmatched. They may not be the most massive or the brightest stars in terms of energy output, but they easily take the crown for sheer volume. Two of the most famous red supergiants are Betelgeuse, which sparkles like a red gem in the constellation Orion, and Antares A, the fiery heart of the Scorpius constellation. These two stars are so bright that they shine with first magnitude brightness, making them stand out as some of the brightest stars you can see in the night sky with just your eyes. Astronomers have a special way of sorting stars. They look at how bright a star is and how strong its surface gravity feels. They do this by examining the light that comes from the star, especially the lines in its spectrum. Those are like barcodes that tell us what the star is made of and how dense its surface is. If the surface gravity is low, it usually means the star is very large and spread out, and that usually means it's very bright too. Even within the supergiants, there are different levels. Some are regular supergiants, some are extremely bright, and others are somewhere in between. For the most extreme ones, those that are incredibly large and losing mass at a wild rate, astronomers may give them a special label like Class 0 or Ia+, which means they're hypergiants, the wildest and most unstable stars. However, the term hypergiant is rarely used for red supergiants, except for especially unstable ones like Viocicanis majoris and NML Cygni, sometimes referred to as red hypergiants. The word red tells us these stars are relatively cool compared to others. Most red supergiants are M-type stars, the coolest in the classification system. A few are K-type, which are slightly warmer, and those are sometimes called orange supergiants, like Zeta Cephei. There are even rarer examples like yellow hypergiants, such as HR 5171AA. These red supergiants have surface temperatures lower than 4,100 degrees Kelvin, which is cooler than our Sun. But because they are so incredibly large, they still shine with tremendous brilliance. A red supergiant can be anywhere from a few hundred to over 1,000 times wider than the Sun. But it's not just size that makes a star a supergiant, it's how bright it is for its temperature. For instance, Alpha Herculis is a cool giant star with a radius between 264 and 303 times that of the Sun, but it isn't considered a supergiant. Meanwhile, Epsilon Pegasi, a K2 supergiant, is smaller, just 185 times the Sun's radius, but it still qualifies due to its intense brightness and other features. Even though red supergiants are cooler than the Sun, they can shine tens of thousands to even hundreds of thousands of times brighter. That's because their vast surface area pours out so much light. The largest ones are thought to reach up to about 1,500 times the Sun's radius. But beyond that size, a star becomes so unstable that it can no longer hold itself together. This upper limit is called the Hayashi limit. These stars don't start out as giants. They begin life as very massive hot stars, with around 10 to 40 times the Sun's mass. As they burn through their fuel, they swell up into red supergiants. But if a star starts with more than 40 solar masses, it usually does not become a red supergiant. Instead, it stays hot and compact, following a different path through its life. At the higher end of the red supergiant range, these stars shed their outer layers at incredible speeds, losing millions of times more material each year than our Sun does. This creates bright, glowing clouds of gas and dust around them, called nebulae. By the time a red supergiant nears the end of its life, it may have lost most of its original mass, often shrinking to around 10 times the Sun's mass before the core collapses. The exact amount depends on how fast the star spins and what elements it had when it formed. These stars are not always steady in their brightness. Most of them flicker and fade over time in an irregular way. That's why they are called variable stars, specifically semi-regular or irregular variables. Some change just a little, while others can vary by as much as 4 magnitudes, a huge swing in brightness. Why does this happen? A few reasons. These stars often pulsate, swell and shrink slightly. They also experience powerful stellar winds and disturbances on their surface. Some show effects of giant convection cells, massive bubbles of hot gas rising and sinking on the surface. These bubbles are far fewer than on the Sun, but they are much bigger and can cause noticeable changes as the star spins. When astronomers study red supergiants using spectroscopes, they see complex patterns called absorption lines. These are like fingerprints that tell what elements are in the outer layers. Metal lines and molecular bands like cyanogen, Cn, and calcium, Ca2, help scientists figure out how big and bright a star really is. Red supergiants may be slow and quiet now, but they are nearing the end of their lives. They aren't the hottest or the most massive stars, but they are among the largest and brightest in the universe. And when their time comes, they end with a bang, a massive supernova explosion that blasts heavy elements into space, helping to create new stars, planets, and maybe even the ingredients for life. Around red supergiants, there's often a cloud of gas and dust known as circumstellar material. Some parts of this material shine in a special way called massa emission, which is like a space version of a laser, but instead of light, it gives off strong microwave radiation. These masses usually come from water vapor and silicon monoxide, and sometimes from hydroxyl molecules, but only in thin layers around the star. Astronomers use powerful radio telescopes like Very Long Baseline Interferometry, VLBI, and the Very Long Baseline Array, VLBA, to study these emissions. These tools can map the area around red supergiants with stunning detail, and even measure the exact distance to these stars using a technique called parallax. This helps scientists understand the layout of our galaxy and discover stars that are hidden behind thick dust clouds. Though red supergiants have burned all the hydrogen in their cores, their outer layers still contain mostly hydrogen. But just before the final explosion, they lose so much material that helium may become just as common on the surface. In some extreme cases, they may lose almost all their hydrogen, leaving behind a helium-rich shell. When these stars first swell into red supergiants, their outer layers usually have more oxygen than carbon, and nitrogen is the least common. But as the star ages, the deeper fusion products rise to the surface in a process called dredge-up. This causes carbon and oxygen to drop and nitrogen to rise, due to a fusion method called the CNO cycle. Red supergiants rotate very slowly, some barely spin at all. Even stars that spun quickly when younger are slowed down drastically by the time they reach this stage, thanks to strong winds and mass loss. A few, like Betelgeuse, still show a bit of rotation. Scientists believe this might happen if the star has a companion in a binary system. Interestingly, while the outer layers spin slowly, the core can still be spinning fast, leading to a big difference between the surface and core rotation. While all red supergiants fall into luminosity class 1, this label can sometimes include very different types of stars. Scientists now use a more precise definition. A true red supergiant is a massive star that starts fusing helium in its core without becoming extremely dense or having a sudden helium flash. These stars go on to fuse heavier elements and finally collapse into a spectacular supernova. Other stars that look similar, those on the asymptotic giant branch, AGB, can also reach up to 1,000 times the Sun's brightness. But they're different. AGB stars usually have lower mass, a different chemical makeup, and behave differently. Instead of exploding, they end quietly, shedding their outer layers and turning into white dwarfs surrounded by glowing clouds known as planetary nebulae. Some red supergiants go through a strange phase called a blue loop. During this time, the star temporarily gets hotter before cooling back into a red supergiant. These loops happen because of a mix of things, like the star's mass, how fast it spins, and what it's made of. During a blue loop, the star's surface temperature can rise to about 10,000 degrees Kelvin. Blue loops are more likely when the core made of helium grows large compared to the outer layers, which causes the star to lose mass quickly. Within just 1 to 2 million years of becoming a red supergiant, the star runs out of helium in its core. Then it starts burning carbon, followed by other heavier elements, one layer at a time. This process keeps going until the core is made of iron, which cannot be used for fusion to release energy. When that happens, the core collapses in just a few seconds, causing a supernova explosion. Once carbon fusion begins, the star has only a few thousand years left to live. Most of the time, the final collapse happens while the star is still a red supergiant. Its outer layers, rich in hydrogen, are blown away in a Type II supernova. Because the hydrogen takes time to cool, the explosion stays bright for a long time. This is called a Type IIp supernova, with the P standing for plateau. The brightest red supergiants, especially those with more heavy elements like the Sun, can lose most of their outer layers before exploding. These stars might turn into yellow hypergiants or luminous blue variables and explode as Type IIL supernovae. These still contain hydrogen, but not enough to maintain the long, bright plateau. Interestingly, scientists have never seen the explosion of the very brightest red supergiants. It's believed that these giants lose all of their outer layers and become Wolf-Rayet stars, hot, stripped-down stars with no outer shell, before they finally explode. Even though red supergiants are enormous, they don't stay that way for long. In fact, they're always quite young stars, no more than about 25 million years old. While that might seem like a long time to us, it's actually short when it comes to the life of a star. Red supergiants are born from very massive stars, which usually only form in large star groups called clusters. So, red supergiants are often found in places where many stars form together. Altogether, astronomers have found 80 red supergiants in just a small section of sky near these clusters. This incredible group of stars is thought to be the result of a massive wave of star formation that happened between 10 and 20 million years ago, near the middle of our galaxy, right where the central bar of the Milky Way begins. Even though red supergiants are rare, they're so bright and so large that we can sometimes see them with the naked eye. Some of them even change brightness over time, which makes them extra fascinating to scientists. One such star, Mira, was once thought to be a red supergiant, but it's now known to be a different kind of aging star, a member of the asymptotic giant branch, or AGB stars. Some red supergiants are even more extreme. These are called red hypergiants, monsters among stars. Their radii can be more than 1,000 times larger than the Sun's. In a major survey of the nearby Magellanic Clouds, two small companion galaxies that orbit the Milky Way, astronomers found about a dozen extremely bright M-type stars. These giants were shining with more than 250,000 times the Sun's brightness, and had sizes starting from about 1,000 times the Sun's radius, with some even larger.